compositions, but I want to take you here. Here are pressure estimates over here from various, from alumina actually, and here are the titanium versus the titanium diagram. And from this, we concluded that the Devsai rocks originated from 875 to 700 degrees centigrade and at 6 to 4.2 kilobar. I think that the temperature estimates are not correct. The 6 to 4.2 kilobar are okay for mid-Cretaceous, middle levels of the crust. But the temperatures are too low, so maybe the... Okay, here is a model. This has been taken from the paper recently submitted. Professor Lin Ding is the corresponding author, and we show various stages of subduction in the Kohistan. Basically, it shows that there was formation of Kohistan arc, as I said earlier on, followed by continental subduction over there, and that was followed by collision between them. The important thing here is, or is one of the important things, that there are signals of slab failure from geochemistry of Eocene volcanics in Gangdesi Belt, in Ladakh, as well as in Kohistan, suggesting that maybe there was either slab breakoff or rollback during Eocene. Okay, I go to a little bit to the origin of the Devsai Plateau. Commonly, it has been suggested that the plateau is related to tectonic processes. Okay, then by volcanic rocks also form plateaus, like the Deccan Plateau, one of the largest. Okay, then we have, so they are linked to the collision between India and Eurasia processes. Then there have been suggestions, for example here, that no, they may be related actually to rapid uplift because of erosion. Erosion was responsible for isostatic imbalance, and that was covered by uplift. But there is another, I saw a paper by Beek et al., which suggests that the plateau did not form due to the previous processes, tectonic closure, or to isostatic uplift underneath, above the subduction zone. But instead, this is only an erosional remnant of the Tibetan Plateau, which means that the Tibet Plateau during Eocene was stretching as far west as Nanga Parbat. That's a long distance for the plateau, but this was proposed that the plateau was eroded, and now a hard core is left because the area is composed of granitic rocks and volcanic rocks, which are not easy for erosion. Okay, I think we discussed that. Okay, the summary is that Devsai Plateau is second highest to Tibet. It is occupied by calcaline, volcanic, and plutonic rocks of Kohistan-Ladakh arc, and the Ladakh arc overlies the Indus-Suchar ophiolite melange. The origin of the Devsai Plateau has been a subject of debate. India-Eurasia collision is one theory, as I said. The other is that there is isostatic adjustment due to rapid glacial and fluvial erosion, or it's possibly a preservation. I think I'm through with it. Thank you very much.
Perfect timing. The next speaker, Professor Erwin Appel of Tübingen University, is going to speak on a cluster of excellence, Terra, possible collaboration with PlateauPlus.
Yeah, good morning, everybody. First of all, let me thank the organizers and the host here for inviting me as a key speaker for this workshop. I very much enjoy these days here in Jakarta, the first time for me in Indonesia. So, of course, when you see the first slide, you will think about what it is. No, that's not. Okay. I will not present research results here. Yeah. I want to go in the direction which is also an intention of PlateauPlus, highlighted here in red, yellow, that PlateauPlus also emphasizes global collaboration, unifying researchers from multiple continents. That means I put my hand on the screen during the inaugural meeting in Beijing, and I think I want to pick up this chance here to try to get a first footstep into increasing the community working together on this platform. So, and Terra, what is Terra? What I mean here? No? I put the first button. Okay. But then it goes quickly. Anyway, let's leave this. There is an excellence, so-called excellence strategy from the German federal and state governments to strengthen the international competitiveness of German universities. And they put quite a lot of money into so-called clusters, excellence clusters or clusters of excellence, which will run for 7 years. This period now starts at the beginning of 2026, and there is more than 6 million euro per cluster for this period per year. So these 70 clusters are across all disciplines, all disciplines including medicine, social sciences and everything. And so it's a quite competitive measure. So, and Tübingen, I come from Tübingen. I'm a retired professor of Tübingen University, and I'm not an active member now, researcher in this cluster, but I stay in steady contact with my colleagues in Tübingen, and I discussed this with them to act somehow as a messenger, to make aware of what is going on. I think this is the first step when you want to go to collaboration, that you know what is going on. And so I decided, in agreement with the colleagues in Tübingen, to present this excellence cluster Terra, which is an excellence cluster in geoscience, mainly in geoscience, and it's, there are only 2 of such excellence clusters in geoscience in Germany. The other one is on marine sciences. So this is a big chance for Tübingen and the 2 other institutions which are collaborating here in this cluster, the University of Hohenheim and the Senckenberg Institute. And we have Andreas Muich here, gave a keynote talk yesterday, who is also a member of this cluster. And you see here the new building, which we got in Tübingen 6 years ago, very functional. And when we look now what Terra is intended, then you see that the aims of PlateauPlus and of Terra have quite a lot in common in principle. So PlateauPlus, interactions between geological and environmental and anthropogenic factors, and integrating Earth processes in different spheres below and above the ground, and Terra aiming at interactions between the Earth's geo and biosphere, or geo-biosphere interactions in the focus. And the difference is, of course, the targets. The target of PlateauPlus is, I This is really annoying. It's on mountain ranges, on plateaus, 6 plateaus, and for Terra it is on underlying laws of nature which always apply. So there is of course a connection when it always apply, when there are processes which always apply, they apply also on mountain ranges, and this is what makes me believe that these two initiatives can be very well connected, or could be very well connected upon activities which are then have to be driven by the researchers involved. We have seen this yesterday by Andreas Mulch. This is also, you can say, part of Future Terra, which is done as research before, and I don't discuss this one. Andreas did it. So the uplift of mountain ranges play a big role, also for the biosphere, which reacts on these changes in the geosphere. Now, okay, let's go with that. When we look on Terra, it's not only looking on the deep processes. We have here a lot of talks targeting the deep subsurface processes. But when we talk about geo-biosphere interactions, of course, these interactions are also on the very shallow, on the very near surface spheres. For instance, as an example here, when the nutrients take up from the subsurface, related also to weathering processes, then this diversity which is evolving here also feeds back into the carbon cycle by burying the carbon into the soils, and this is one typical example, just explaining what the geo-biosphere interaction should mean. So there are multiple possibilities of looking on geo-biosphere interaction. If it goes forward, okay. The research themes in Terra, it looks into the geological past, what we have seen yesterday in terms of uplift of mountain ranges. It looks into contemporary geo-biosphere interactions in a large scale and in a small scale, and what is known from these researches should also go into future prospections. This is another example of uplift related geo-biosphere interaction. Andreas also showed this or part of these figures yesterday from a paper of papers of Mort Myers, who will join Tübingen University very likely within the next couple of months, and then continue also the work in this direction related to mountain uplift. I just emphasize this because, of course, the geo-biosphere interactions, as I have shown in a slide before, relates also to very near surface processes of geo-biosphere. This is an example which will continue, which relates the geo-biosphere interactions to the deeper processes of the geosphere. This is also from this group who then related the faunal and flora turnover here in the Anatolian Plateau to surface uplift. Okay, what else will be done, is intended in Terra? For instance, this is an example. There will be some examples now. There are no results. This is intention. And for instance, here in these large-scale contemporary geobiosphere interactions, it is looked on what happens when you have a big flooding, for instance, and how the biosphere is re-establishing and recovering after such a big flooding. So in terms of cycling of the water, of matter and elements involved. Another example here, what happens when the glacier is retreating, and how this glacial retreat and the peatland formation, which is related to this land surface evolution, is going on, and what are the controlling factors for carbon sinks, what determines resilience to climate extremes. This is an intention of projects looking on the landscape evolution, including provenance, uplift rates, erosion rates, and remote sensing. And this is something which now in Tübingen is done on very old rocks, but it can be very well also done in mountain areas, on plateaus, everywhere in the world. And it is confirmed that there is interest from the Tübingen side to also do such studies in the Alpine mountains, which are considered as one of the 6 plateaus in PlateauPlus. Then there are natural baselines which have to be investigated, like the climate evolution from such sedimentary archives. And when one looks to the future projections, then the paleo to future approach has to look into what happened in the past. And this is one of the possible reconstructions of the global temperatures. And there are several past temperature events which are important for future prospections, depending on what is predicted for the future global warming. And for instance, the Miocene conditions are now in a focus, because for not a limited warming to 1.5 degrees centigrade, then it is very interesting to see what happened with the geobiosphere interactions in the middle Miocene, where the temperatures are maybe or were maybe very similar to what we expect for the future in our lifetimes. Or very fast, rapid changes in the last glacial, what does it mean for geobiosphere interactions? So looking further back, then we have weathering effects of global cooling, which lead to biosphere reactions in forms of sea plants and developing of savannas. And when we go to these future predictions, then one has to look on very different scales here. For instance, here, when we have CO2 release into the atmosphere, we know it will warm up the global climate. Microbes grow better in warm climate. They are producing again CO2, and this increased CO2 feeds back into more stronger warming. And these processes all have to be understood. So this is also demanding for a quite large activity in modeling using different approaches with uncertainty quantification, also with looking into so-called ecometeorology relationships and biogeochemical cycles which are related to the land surface cover, natural or man-made. Not all, of course, is related now in Terra to mountains. That becomes clear, but mountains are involved already in the focus of Terra, and it could be increased if the people come together and working on principal laws of what is happening in nature in terms of geobiosphere interactions. I think something valuable can evolve here. Also, the outreach of PlateauPlus and Terra have a lot of similarities in terms of their usefulness for society. So, at this stage, where Terra and PlateauPlus already exists since 2 years, but Terra now will start at the beginning of 2026. There is a lot of flexibility in such an excellence cluster. Such an excellence cluster like Terra is not a fixed research program. So there are no projects which are evaluated as such, and then you work on these projects. It's a research framework. And the cluster itself then acts as a mini funding agency and can decide on projects by itself. So taking up the opportunity to work together and to communicate also gives us a lot of chances, or could give us a lot of chances to develop a closer connection between these programs, and I understood that this is something which PlateauPlus is having as one of the intentions. Additional members can be included in such an excellence cluster upon suggested projects. There are also a large portion of the funding invested in structural measures, which improves the possibility of doing experimental work. Just a few here shown in pictures and mentioned. This is something the biologists, the agricultural people are planning in terms of setting up such a diversitorium with an experiment where the precipitation and the ground conditions can be modulated to see what is happening in the biosphere when you change the geosphere. So these are the people here involved in Terra. You see Andreas here in the second row. And you find all this material on the website when you are interested to get in contact. And by just searching here for Excellence Cluster Terra or Terra Tübingen, you will get the information you need to make a first step into a potential collaboration to make the people interested. And I consider myself as a messenger here. No? And I'm, of course, willing, when you contact me, to help to establish contacts. And I would be very happy when Terra at the end becomes one or part also contributing to PlateauPlus. Thank you.
Thank you, Erwin. As a geochronologist, I really appreciate people staying on time. The next talk is by Paul Valdez from the University of Bristol. Role of orographic controls on past changes in climate, biodiversity, and ocean biochemistry.
Okay, good morning, and again, thanks to the organisers for this splendid meeting, and also it's been delightful. It's my first visit to Indonesia, and so I've had great fun here, and it's been really lovely to see the countryside and meet the people. So what I want to talk about today, or what really we're a double act here. So I'm talking first, Alex is talking afterwards, about using climate models to help us understand the processes that are important for how mountains influence the whole of the climate system. What I'm going to talk about is a very big picture approach, looking at the broader aims in a way of PlateauPlus, and Alex is then going to focus in on a much more specific and more realistic example. So I've lost my pointer, so can I have the next slide? Yeah, good. So you saw a version of this, I think, in Andreas' talk yesterday. We know that mountains have a huge impact on the whole of the Earth system. The atmosphere that clearly has a big role in it. They've taken it. I think the batteries have run out. So I've got the pointer, but I haven't got the flicker. A changer. Yeah. Yeah, I got that bit working. I think they're doing a battery. So we've got lots of different components of the Earth system, and the mountains are playing a clearly incredibly important role in all of these different processes. But I would argue that it's impossible to really work out how the different feedback processes work without, without having some form of model that allows you to do sort of experiments. And so the model that for those of you not familiar with climate models, the climate models work on the basic physics of climate. We're literally solving Newton's laws of motion as they apply to the atmosphere and the ocean, indeed also to the cryosphere. We also have equations these days for thinking about how the biophysics changes within the Earth system. The problem is you can't solve them with pen and paper. You've got to go to computer, and when you go to computer you make approximations, and that leads to uncertainties. So they're not perfect, and so I always like the quote on the right there: never tell me my model is wrong. I know it's wrong. It's a model, it's not reality. But I do think the models now have a level of usefulness that allow you to ask questions that you just cannot do from data alone. And that's what I'm going to talk about. So, in particular, what I want to do is I want to ask the simple question of saying, well, what is the role of mountains in the climate system? And we can do that in a climate model by doing what-if experiments. And the what-if experiment I'm going to be talking about is that I'm going to get rid of all the mountains. They're gone. So on the right, on the left is our normal representation. Got the wrong thing there. On the left is our normal representation of mountains. The right is a flat Earth world. That's the only thing that I'm changing. I'm not changing the bathymetry, I'm not changing the CO2 level, and that's actually an important point in all of these calculations. I'm not thinking about weathering processes, so I'm not including weathering, but I'm including lots of other things. So let's have a look at the results. What does climate model say? And first of all, if we look at the top panel, this is the normal temperature distribution that the model predicts. This is now the temperature distribution without mountains. And I think the first thing that is really incredibly striking is just how zonal the temperature patterns are. The temperature contours are almost lines of latitude now. There's very little in the way of departures from zonal symmetry. And that's, in one sense, I would argue, is quite surprising, because although mountains we would expect to play a role, the climate system, or the land in particular, is much lower thermal capacity, and so you would expect it to warm up more in summer and cool down more in winter than the ocean. And lo and behold, if I was showing you the seasonal patterns of change, you would see that. So at the seasonal level, there are still temperature gradients between land and ocean, but they literally completely cancel out. So in the annual mean, which is what I'm showing you here, you just see lines of latitude. And unfortunately, time means that I cannot show you all the seasonal details as well. So I'm just, on all the plots I'm going to focus in is the annual means. Down below is the difference between these two plots, and in particular I've plotted it in the sense of saying this is the climate with mountains, climate without mountains. So what you can see and to understand the sign of the thing, it's saying that if you add the mountains, then lo and behold you get most of the land is colder, and of course that's just because it's elevated surface and makes it colder. But the thing that I want to really emphasize here is the fascinating thing of saying that the oceans are actually warmer because of mountains. And so why is that happening? Well, to understand why that's happening, you need to look at the ocean circulation. What I'm showing you here is the ocean circulation. It's a cross-section through the ocean, so this is depth, and this is from the south to the north. I'm showing you a cross-section through the Atlantic and the Pacific. And what I'm showing you is its so-called stream function, and basically the flow of water follows the contours around. And so this is telling us that you've got, and when it's orange and red, it's clockwise, and when it's blue, the circulation is anti-clockwise. And what you can see is that in the present day, we've got a very strong circulation in the Atlantic, but that completely changes when you get rid of the mountains, and you no longer have the Atlantic overturning circulation, you no longer can transporting heat towards the pole. By contrast, the Pacific has a huge change. So there's major changes in the ocean circulation driven by the changes in the mountains, and that is the thing that is causing our sea surface temperatures to change. So why is the ocean circulation changing? Well, the ocean circulation is changing because there's a major change in the hydrological cycle when you change the mountains. This particular plot is probably not the only plot I should have shown to explain the oceans, but it's a readily recognizable plot. Again, we've got precipitation, the annual mean on the left, or with mountains and without mountains, and this is showing you the difference field. And you can see that there are huge differences. So if I plotted it as a percentage, we're talking about percentage changes which are typically, can be up to 50% of the total amount that is normally received. So we're seeing big temperature, precipitation changes, and those precipitation changes, or particularly the net hydrological cycle, the precipitation minus evaporation minus runoff, is the thing that is changing the buoyancy flux to the ocean, and that is changing the ocean circulation. So it's the hydrological change which is the key component to the system. But my abstract talked about not just climate, but we also talked about vegetation, and so how does the vegetation change? And because I'm a bit short of time, let's just focus in on the net primary productivity. I've got here the different types of vegetation that the model represents, but if you look at the net primary productivity of the vegetation, you get the same story that you saw for the temperature, basically. That although that there are seasonal changes going on and there are changes in the precipitation, the dominant thing, particularly in terms of mid-latitudes, is you go from quite a structured pattern over the continents to really quite zonally symmetric, zonally smooth pattern emerging. A little bit more structure, I guess, in the tropics, because in general vegetation in the tropics is more sensitive to precipitation changes. So there's some big changes in vegetation by the mountains. Again, not surprising. What about the marine system? So I've just chosen one of the parameters out of our marine ecosystem. And what's interesting there is actually the marine ecosystems aren't responding so much to the changes in mountains. You know, to first principle, although there's some changes, there's important changes in the Atlantic, and that's because of the ocean circulation changes. Otherwise, what you can see is that the patterns are really quite similar between the simulation with mountains and without mountains. And the reason for that is that actually the mountains, these where zooplankton is growing is very strongly influenced where upwelling is, and upwelling is very strongly controlled by just the wind pattern at the surface, and those wind patterns over the oceans aren't changing quite so much. Over land they do, but over the ocean they're not changing quite so much. So we're not seeing so much differences in the marine ecosystems. However, you are seeing differences in ocean biogeochemistry, and particularly if you look at the oxygen concentration, this is at 2 kilometers depth in the ocean. This is ocean with oxygen with mountains, oxygen without mountains. And you can see that those changes in the ocean circulation makes a huge difference. In our modern world, we have the Atlantic is relatively oxygenated because there's deep water forming. That's completely changed and reversed, and in fact now the Pacific is the one that has high oxygen levels. So there's a big difference there. But note that that we aren't talking about the ocean going anoxic or anything like that. It is just a change in the pattern of oxygen. So there's big differences. In one sense, I guess you're not surprised. I'm not the first person to have done these sort of type of simulations, although I think we're the first to actually have these marine and terrestrial ecosystem models in there. What I now want to do is ask a question of saying, well, what are the drivers? Which are the plateaus that are important? PlateauPlus is meant to be looking at a variety of different plateaus, so let's have a look at the different plateaus. So I've kind of repeated my what-if simulations. Next slide. I've gone twice. Back. That's it. Good. Okay. So what I've done this time round is instead of getting rid of all mountains, I've just got rid of Tibet. Let's imagine a world where there's no Tibet. It's not a very nice imagination because Tibet is a very beautiful place. But let's see what is the climate like if you just get rid of Tibet. And so here I'm just going to again show you just the annual means. I'm showing you the change in temperature and the change in precipitation. I've used the same consistent sign that's saying that I'm showing you the mountain minus no mountain case. So you can see a very big response, obviously a very big cooling because of Tibet sitting there. What you can see, of course, what again we're not at all surprised about, is that the Tibet is driving the Asian monsoon very strongly, and so you can see a very strong response in terms of precipitation. What's also perhaps people aren't so familiar with is that what we always see as a robust feature of climate modelling is that you also see a dry region surround it, particularly over the sort of Africa, Eastern Africa and Arabia, and that's a very well-known mechanism called the Rodwell-Hoskins mechanism, where basically the air that's coming up in the monsoon goes down in that region, and that causes it to be dry. And so that's very much a local response. But you can also see that there are far-field responses. You can see in the temperature field there's so-called Rossby waves, planetary waves, which are propagating from Tibet and crossing the Pacific and into the North America and the Atlantic. That's also having implications because what you can see is that we're seeing differences both in the North African monsoon, in the South American monsoon, indeed also in the a little bit in the North American monsoon, just from changing Tibet. So big consequences. However, there is a caveat that I need to make on this sort of calculation, in the sense of saying it does depend a little bit on how you do the calculation. If instead of what I did was I removed Tibet from a model which otherwise had mountains, if I did it the other way round of adding Tibet to a flat orography, then my conclusions are slightly different. And particularly, what's interesting is that the local response is very similar. So again, you've got a big impact on the Asian monsoon and a big drying over Arabia and East Africa. But the far field response, and particularly what you can see is in this case, you get a big change in the Atlantic and in the southern hemisphere. So the teleconnections, these far field responses, are quite sensitive to how you do the calculation or the assumptions that you do. And I highlight that particularly because there was a paper came out last year, and they did similar to what I've been talking about, but they gradually added it from a flat world. And so we get very similar results to what they get, but we're getting different stories. So the far field response is a little bit sensitive to how you do the calculation. Let's quickly now go over the other mountains. Here's the impacts of the Rockies, or rather the Colorado Plateau. Nowhere near as dramatic or large scale as for Tibet, but you can see a very big changes in the vicinity of North America. Again, there are some planetary waves, Rossby waves, which propagate out from that, which have an influence, you can see, particularly on the North African monsoon, a little bit on the Asian monsoon, again through a global teleconnection, but really quite modest. Do the same thing for the Andes. Oops. I think it's going to suddenly flash through. It doesn't want to move on for some reason. That's the Andes now. So the Andes, again, always you get a big effect locally. The Andes have a big effect in terms of the South American monsoon. It has a big effect also on the North African monsoon, but less so going through into the Asian region. I could carry on. I've got the whole suite. I'm just going to go one more because I haven't got time to do everything. But I just comment about Antarctica. So Antarctica, if you change Antarctica, if you get rid of Antarctica, then clearly there's a big effect in the vicinity of the southern hemisphere. But what's interesting is actually by the time you get into the northern hemisphere, there's, the temperature changes are quite sort of zonal again, and very little impact in terms of the precipitation. So Antarctica is important for the southern hemisphere, but actually for the monsoon systems, we're really not seeing a big response from Antarctica. I'm going to, as I say, unfortunately I've got Africa. I also got the Iranian Plateau, but I'm going to have to go over that and skip over that because I haven't got time. What I do want to do is finish off by saying that so far I've talked about the big mountain ranges. What about sort of more detail? And again, it's not one. What about the Himalayas? So far we've looked at the big plateaus. What about just a smaller, narrower mountain range, but clearly incredibly important? What's the effects of the Himalayas? And so again, you can ask that, and Alex in particular has done a really nice study. This time it's a much more specific study looking at the particular time period in the Miocene, and he's imagined a world where you've got Tibet there, and you start off basically with barely any Himalayas really. On the southern flank of Tibet, there's nothing there at all, and you gradually increase the height. The only thing that's changing is this arc of mountains, Himalayas, on the southern flank of Tibet, and it's eventually we run it for up to 7 kilometers. So let's have a look to see what the response is. And the first comment is to say that actually there's not much of a signal globally, but locally there is a very big signal. And what I'm showing you here is, so the height of the Himalayas is going from low Himalayas to high Himalayas up here. And what you can see is that as the Himalayas rise, Tibet gets drier and drier. And that has a big impact on the vegetation patterns in the region, which fits with some of the data that we've had. But the thing that's particularly interesting about these simulations, which I think is very important, is that it is really very much, Andreas mentioned it, in his talk, is that there's very much a tipping point in the height. So, it went too quickly, go back. There you are. It's that what you see is that as the Himalayas rise, you get to 5 kilometers, really doesn't make much difference. 6 kilometers, barely any difference. But somewhere 6.5 kilometers, you suddenly get this incredibly strong drying effect. It really is a tipping point, a threshold behavior in the system. And so it's a really marked and a challenging thing, therefore, to model. So I better finish there. I just want to say that in some senses I think my talk is basically telling you what you know already, and very obvious, namely that mountains are incredibly important for the climate system. They have big impacts on the monsoons, they have big impacts on vegetation, they have big impacts on oxygen levels in the ocean, even without thinking about weathering. Maybe the marine ecosystem is a little bit less sensitive. We saw that Tibet was by far and away the most important of the mountains, but the Rockies, Andes, and Africa, Iranian Plateau, all play a role. And particularly if you're, rather than interested in the Asian monsoon, if you're, for instance, interested in the North African monsoon, you have to think about all the mountain ranges. There seem to be, the North African monsoon seem to be sensitive to all of the different mountains. But before I finish, I've got 4 seconds, so I'm going to have to do it very, very fast. But just to say that I want to advertise the fact that we've got a new project started. It's an SFC-funded project starting in January, based at ITP-CAS. And what we're looking at is we're going to do kind of similar work to what I've shown, but in a much more refined sense, where we more gradually and more specifically change mountain ranges around the world and look at the consequences of that for climate and for biodiversity. I would argue that this project is very much modelling support for PlateauPlus, and I'm recruiting postdocs, so if you know good paleoclimate modellers, please send them in our direction. And with that, I better finish. Thank you.
Thank you, Paul. Small change in plans. Our next speaker has just, I think, arrived from the airport, needs a few minutes to get his thoughts together. But what we'll do is, since we're running a little ahead of time, is let's take 10 minutes to have a discussion of the last 3 keynotes, and then we'll take the scheduled break. So any questions about any of the 3 speakers? Here we go. Okay, let's go. Jindeng? Just belt it out.
Have a question for Paul's very interesting talk. So when you remove the mountain, I found the vegetation, their distribution is a little bit tilted relative to latitude. Did you notice that? It's not like exactly like horizontal. Why is that? That's my question. Thanks.
So that is, I think, the continentality effect. That actually, as you go into the continent, it does get drier still. That even without mountains, you're still seeing a bit of that effect going on. So I think it's kind of related to that, but I'd have to look in more detail to be exactly sure that that's what's going on. But certainly, you do see a little bit of continentality effects even with the vegetation.
Okay, thank you. I also have a question for Paul. Thanks for your great talk. Actually, I was thinking that you just thinking Himalaya separately. Would you consider about if we list Ganges, the Trans-Himalaya, the Ganges also separately, how the climate impact? I'm not sure. Yeah, just a suggestion maybe. Yeah. Okay, thank you.
So what do you mean exactly?
I mean, if we just consider the Ganges, Ganges mountain, there are 2 mountain range, the Himalayas and the Ganges. Actually, the Ganges, according to Professor Dean's research, that it uplifts much earlier. So I think if we just consider about the Ganges, it will give more insight about the paleoclimate, especially during the early Cenozoic or later Cretaceous and like this.
Okay, I understand now your comment, and I absolutely agree with you. The results I was showing you were very much focused on the Miocene, where it's more related to the Himalaya. But Ganges is certainly going to be a very important thing, and that is going to be very much the sort of thing that we're going to be looking at in our new project. We'll be looking at that for the early Cenozoic as well as changes in the later time periods as well. So, and you're right, I think you would see a lot of similar effects in some senses and potentially another threshold, but we would have to do the simulations before we know what they are.
I have a question for Professor Kasem Jan. And from your talks, you said that the structures and the geochemistry of the Desai Plateau is actually quite similar with the Ganges. Does that indicate that the Desai Plateau uplifted to high elevation during the late Cretaceous or to the early Cenozoic, just like the Ganges Mountains? Thank you.
I don't know, but there is a lot of volcanism in Gangdesi Belt, which is older than Eocene. I mean, it goes all the way to Jurassic and very late Triassic. But the later phases in which perhaps the Gangdesi batholith was developed for mostly toward the end of Cretaceous and early Tertiary. And if you remove the Karakoram fault between Gangdesi Belt and Ladakh, it's likely that they would continue as a single complex batholith all the way from Kohistan through Ladakh to Tibet or Gangdesi Belt. This is from their location, as well as after you remove the Karakoram fault and you look at the chemistry of the batholith in Gangdesi and elsewhere, there are great similarities. So we believe that there was a continuity of the Tibetan Plateau, Western Tibetan Plateau, all the way up to Nanga Parbat at least, where when Nanga Parbat started arising and split it into two. Okay?
I'm co-author of the paper. The Ladakh and Kyrgyzstan is equivalent of Ganges Mountain in the West. So maybe they have same rife history. I also had two questions. First one for urban airplane. It's possible the PlateauPlus can be part of the Terra, can be a cluster of the program. And I understand it is your domestic project. Can we be part of the cluster or can be a cluster of the program?
Yeah, that depends on what you understand as be part of the cluster. Of course, from the side of the budget, not, yeah, but from the side of the collaboration. This is what I wanted to stimulate here, that the community becomes wider, no? And this concerns the plateaus worldwide. Yeah? South America is not at all represented here, and this concerns about geobiosphere interactions in general. So in this workshop, the geobiosphere interactions are a bit less represented, yeah? But it's an aim of PlateauPlus, yeah, to look on the interactions between the spheres. And so the programs which are running worldwide should be aware of each other, and this will help to establish cooperations. That was my intention.
Yeah. Anyway, can Terra funded the PlateauPlus in the future?
Yeah, certainly not.
Okay, my second question is for Paul. I want to know your opinion. Is the Himalaya or the Tibetan is more important for the South monsoon in different stage?
So in practice, I think that's really a question you should ask Alex. He's not done so many simulations on this. Then I think the reality is that it's a bit of both. What you saw with the Himalayas in particular was that it had a big impact in terms of how the monsoon spread out into Tibet itself. And so that's clearly incredibly important. What you also saw was actually that the Himalayas had less effect on the global climate system. But to actually answer that question, I think really does require you to be a little bit more specific. And it's you know, all of our research says that we shouldn't think about just one evolution of the Tibetan plateau. We've got a lot of different structures going on, and each one of those has an influence on the monsoon. So I think, I hope I do Alex's research justice there.
Any more questions?
I have also, okay.
Thank you.
Okay, thank you. My question is to Paul. In your model, you changed the surface topography, but how about the ocean topography? Have you considered it in your model? Thank you.
Yeah, so in those, the simulations I showed you, we didn't change it. It's got a realistic modern-day bathymetry in there, and we didn't make any changes on that side. So we are literally seeing just what the terrestrial mountains are doing.
Yeah, I have a question regarding Antarctica. What did you do with the 2 kilometers of ice cover?
Yeah, so again, in this particular calculation, I was very simplistic. I literally, we still had an ice cover. We had an ice sheet which was at zero elevation. Okay, obviously the real world, if the ice sheet melted, it would be a very different story. So again, I was living in Moggle world. It was an idealized simulation, not in any sense realistic. But I should say that sort of conclusion that Antarctica doesn't do much, particularly in terms of the monsoon systems, is something which I believe is really quite robust from the modelling perspective. A lot of different climate models have shown the same story. Actually, Antarctica does a lot locally. It has an impact on the global temperature. It has an impact on the carbon cycle. But actually, as a direct effect on the monsoon, doesn't seem to be very important, at least in model world.
Well, in fact, we are exactly on time. I'm going to end the session now. It's 10:15. We'll reconvene in 50 minutes at 10:30, and we'll begin with the last of the keynotes. Okay, thanks very much, and thanks to all the speakers.
So, thank you very much for all three speakers. Now, we will heading to the coffee break time. We already served the snack and coffee for all participants, but please be on time. It's only 15 minutes. After 15 minutes, at 10:30, we will continue the session for the next keynote speaker, Professor Sin Lee. Thank you, and enjoy the breakfast. Enjoy the coffee break. I'm sorry.
bilangnya untuk semua orang yang partisipan gitu ya. Kalau ini kalau perkenalkan malah aku lihat dari sini dulu.
Sensi lah.
Nomor gue dari mana? Warisan ultima tuh. Nah, makanya. Ada yang lulus gak lapor. Giliran berangkatnya ngapain? Gue buka deh. Enggak bisa dong. Enggak. SOP aja minta rekomendasi. Mana dia ngomong ke siapa? Kalau ngomong apa? Emang gua titipan ekspres. Tapi orang banyak belas rumah di sini. Ya kan kalau besok. Ada Sarawak. Balik bersama itu. Tinggalnya di mana? Lebih perlu. Tahun depan, Januari, tahun Februari, tahun Desember. Sidangnya kapan Pak? 2 tahun depan. Enggak open kali. Berapa 5 tahun? 6. Kalau 6 nggak boleh deh. Aku sudah dibuka kalau nggak dimaksud. Yang sekarang juga awalnya kita pernah. Makanya. Setelah ruangan aja nggak mau. Yul. Kemarin ya Pak, ya atau nggak pengen ke balik ya? Biasanya gitu kalau udah ngerti. Cuma kalau UCL ada dia gabung sama master. Orang ini semua pasti ke London. Ya terus kan landingnya di mana Pak? Seludip ya Allah, nggak ada di. Kalau landingnya Heathrow sekarang memang sudah dekat, tinggal kapas dikit. Enggak, jauh kalau dari Heathrow, kalau dari Gatwick. Oh iya, tapi tinggal niat sih. Yang enggak niat yang nyamperin. Bener sih Pak. Yang dari Edinburgh aja nyamperin ya. Mas Hasan nyamperin Bu. Itu tinggal niat apa enggak? Kalau Mas Hasan minggu lalunya tuh baru dia tahu. Datang itu jam 1 malam. Oh. Seniat itu loh. Aku awalnya nggak tahu Pak ada rombongan itu. Kamu nggak tahu. Terus baru lihat story-nya Bang Tio sama Mas. Oh, apa di sana? Kamu tahu nggak? Aku kenapa nggak kabar-kabar? Bisanya nggak tahu cuma siapa lupa ya, pokoknya sore aku tuh di STM kaki aja tapi udah mau koper udah siap. Iya bukan duit buat tapi baju udah bawa, pokoknya koper udah siap, udah standby di STM kaki. pokoknya yang dikabarin mas keluar pesawat jam urusannya kegiatannya siap ya betul aduh ini kan saya tahu kan udah biasa ya kayak cuma gue gak pernah lihat enggak aku nomormu yang lama kalau izin lu kemana ya aku sering lihat ya nomornya nggak aktif coba ya itu juga aktif tapi kan dulu kau bilang nomor satunya kan tapi nomor satunya nggak aku simpen aku ada ngechat bapak kok di nomor satu iya tapi data simpen oh kali itu juga ada cuma itu HP-nya dalam mode jadi jarang kebuka. Oh ada nih ini nomor satunya BMKG PGN Akmal Firmansal mana goblok atau yang masih sering kontak dengan Mas Hasan karena riset ya? Ya kalau saya udah pusing nanti kita Mas zoom mana promotor itu kan orangnya harus subscribe lagi dulu terus Hasan bukan yang bener ya paling enggak banyak tahu sampai dulu tolak revisi apa ya ya ngasih pokoknya biar ngilang stres juga sih ada titik Jakarta ada aku mikirnya bapak udah di STNKG
Already update just 2 months, just morning I called.
Did you send in the email?
No, I called to you.
Oh yeah, okay. Yeah. Thank you very much. Yeah. Baju tahun lalu? Iya, udah banyak. Main lagi. Nanti aja, maksudnya biar lu lewat aja. Diinjek lagi ya apa? Belum. Belum ada. Aku pengen sih main ke sana. Aku memang sengaja. Baru terbit besok, tapi yang undangan biasa. Besok? Oh iya. Kirim dari situ. Yang undangan ke itu tanggal 29. Beda nggak? 30 bang.
For all participants, I hope you enjoy your coffee break. Now, we will start the next presentation from the last keynote speaker in about 1 or 2 minutes. Please be seated and waiting for the next confirmation. Thank you.
Okay, we're getting back underway. I guess what we're going to do is I'll introduce our next speaker, our next keynote, Professor Xin Li from CAS, who's going to speak on Plateau data, integration, development, and sharing of scientific data at the National Tibetan Plateau Data Center. And then we'll immediately shift to the session 3. I think we need to get going, yeah, please return to your seats, folks. We're getting underway. I was just told by this chap to get up here and do it now. Okay. Okay, so we're getting from the slides and okay, get the last keynote. But I think it makes more sense for you to just put this and just seamlessly go into this. I don't mind either way. Yeah. No, let's do this. Let's have Paul take over now. Okay. And we'll bring up Professor Lee, and we'll get underway.
Okay, so after the
Straight in.
Straight in.
Yeah. And we won't have questions until the end.
I think there was a scientist that
Okay, there's those awards to the...
Let's do that just before lunch.
Okay.
Just before.
Yeah, okay.
All right.
Okay.
Yeah, so that moves forward, but the pointer is on this, and this has to... Okay. Yeah. Sometimes you have to push it twice.
Okay, shall we get going on the next session? First of all, we're going to continue with the keynote presentations. Professor Lee is going to be talking about plateau data, integration, development, and sharing of scientific data at ITP.
Okay, thank you very much, Paul, for the introduction. Okay, first I want to express my warm congratulations to the second PlateauPlus workshop. I still clearly remember the first PlateauPlus workshop taking place in Beijing last January. It's a very nice memory. And the second, I want to thank the organizer and Professor Ding for inviting me here to give a keynote to introduce how to go to the previous slide.
Oh, this one small box on the
some back. To introduce the National Tibet Plateau Data Center with my colleague Professor Xiaodu Pan, and also my colleague Professor Fenming, who is sitting here with the audience. We are affiliated to the National Key Laboratory of Earth System Science and led by Professor Ding, and also we are affiliated to the National Tibet Plateau, also called Suitable Environment Data Center. So the title of my talk is Integration, Plateau data, integration, development, and sharing of scientific data at the National Tibet Plateau Data Center. Here is the outline of my talk. I will briefly introduce what is TPDC, what is our mission, and then I will introduce some data integration and data development and some flagship data products within this data center. And the next part, I will propose how to do good data governance to the AI era. So first, the introduction of TPDC. It's featured on the cover of Bulletin of American Meteorological Society. Plateau data is a new model of big data. It is all the third pole. We try to encompass data with observations and also modeling to serve the plateau research, not only Tibet Plateau, but hopefully other mega plateaus in the world, so-called PlateauPlus. TPDC is the only data center in China dedicated to promoting scientific data of the Tibet Plateau and its surrounding regions. It's one of the first 20 national data centers approved by the Ministry of Science and Technology of China in 2019. We fully follow the so-called FAIR principle: fundable, accessible, interoperable, and reusable. So far, we have more than 100,000 users, registered users, and we share about 8,000 data sets, and about more than 60% of this data are fully accessible, means even without registration, you can download the data from this data center. I could encourage our colleagues here and other colleagues who are studying Plateau to download data and also sharing your data at data.tpdc.ac.cn. So mission of TPDC is try to be an innovator and a leader of data science, both of big data revolution, data platform to facilitate sustainable development, data bank of national research and development programs, and the data bridge that facilitates international cooperation. This is very important. And the data hub outreach to public and data engine to promote entrepreneurship in this region. So objective of the National Tibet Plateau recently is try to break through the traditional concept of data sharing and constructing a cloud platform of data acquisition, visualization, analysis, and modeling together, and try to shift from monolithic centralized architecture to decentralized deployment by setting up data interoperability with domestic and international data centers, for example, data center here. So we will integrate big data analysis, so-called AI and machine learning method with Data Hub, try to support scientific discoveries in this region and other plateaus, as mentioned earlier. So far, we have been certificated by Spring Nature. For example, we are the first data center in China certificated by Spring Nature as a scientific data repository. Means if you are submitted a paper to Nature sister journals, you asked by editor to put your data in a data repository. I could encourage our colleagues here just to put your data, share your data at this repository. We are also trusted digital repository of the AGU, ESSD, led by EGU, and also Data in Brief. We are also the first Chinese member of Enabling Fair Data program, led by AGU. We fully respect the intellectual properties. For example, for each data set, we have a digital objective identifier, and this data should be mandatorily cited by other colleagues who used your data. And we also provide, for example, citing related associated papers. We would encourage our data user to not only mandatory cite your data, but also mandatory to cite associated papers. We also try to boost not only plateau data, but surrounding area geoscience data sharing. In this sense, we think data centers are among mediators that link policymakers, data contributors, data itself, and data users in the ecosystem of data sharing. So more details of introductory of this data center can be found in two cover paper of on the booting of American Meteorological Society, and some introductory and opinion paper published on Nature Geoscience and other journals. So next part, I would like to introduce briefly the data integration, data development at TPDC. We try to integrate data from in situ observations, for example, the field stations, the analysis data from the laboratory. For example, we have good instrument, we have a lot of experiment, and also as well remote sense data. We also try to archive the data set developed by national key project and international projects. Here is a distribution of our multi-discipline data, for example, for cryosphere, for paleo-environment, for human nature relationship, for solid Earth atmosphere. You can see we are integrator of data from Earth system size perspective. Here is slide just to show we have a so-called precise near real-time data integration system of field station data. The real-time, long-time data observed by these in situ observations, for example, automatic meteorological stations and eddy currents can be analyzed, quality controlled of data in a near real-time fashion. We also try to provide a data service for key research projects. For example, for the second PlateauPlus scientific expedition, here is just the introductory homepage for this project. As well as this project, so-called suitable environment study for green security. You can see we are not covering data of plateau, but also Iranian plateau and other highlands in the world. Hopefully, we also hope we can have some data contributions from this very important area. International cooperation is a key priority of the TPDC. We have developed good cooperations, for example, with WCRP World Climate Research Project, GREX project, CODEX project, and we have we provide data service for the ANSO. ANSO is a secured science organization, and we also we provide data. We try to provide good data service for PlateauPlus. We just hold the international PlateauPlus summer school this summer in the Linji, very nice city of Tibet Plateau. Here is a slide to show we have signed MOU with ECMO, and we have data interoperability with ECMO, means regional database of ECMO. You can just download, you can have data service from RDB of ECMO just from TPDC. Here just show some we try to provide data archiving for high-profile articles, for example, for environment change, for Anthropocene, led by Professor Fa Chen, and also lithosphere, the coalition and uplift research led by Professor Ding. You can see for each data we do have a unique DOI. You can just access to that data. You can also download the associated paper related research from our website. I just show some examples. Here is some example of tectonic and geophysical data sets of not only Tibet Plateau, but pan-TP areas. You can see for Central Asia, for the whole Asia continent, and for the Southeast Asia. We do have some, for example, some geological minor data. We have lithosphere data. We have other kind of data already integrated, archived in this data center. As I mentioned, I would like to emphasize this again. We strongly encourage you to share your data, original observation data, integrated data set, and also modern data set as this data center. Recently, we tried to develop so-called AI and machine learning aided data products development for the cryosphere, for the paleo environment. I would like to just show some examples of permafrost distribution of high-resolution forcing data, solar radiation data, and other quality-controlled observational data at this data center. Here is an example of the so-called high-resolution forcing data for air temperature, for humidity, for precipitation, for radiation. This data has been downloaded many times. It's a very highly cited paper, associated paper. Here is another example developed by Professor Feng Ming, who is sitting there. He led a team to develop so-called rock glacier data, talus data, and alpine water bodies data with very high resolution, for example, a few meters to 10 meters. For example, we found that there are more than 113,000 rock glaciers distributed in the Tibetan regions, far more than previous investigated results. Here example of how we developed high-resolution permafrost data, active layer depth data, and the ground temperature data of the Tibet Plateau and the surrounding areas, and also the whole North Hemisphere. You can, from the DOI, you can see all the data are downloadable. You can use for in other research. Next part, I would like to very briefly introduce our recent progress and perspectives within TPDC, this AI region. Together with Professor Feng Ming and other colleagues, we proposed to integrate this kind of advanced big data analytics, for example, big data assimilation. Not only a simulator of in-situ data, of remote sense data, but also, for example, social data. Also integrated deep reinforcement learning, causal inference into with various kind of big data to develop some kind of high resolution digital twin of this region. This is our perspective. Just some details. For example, within this key laboratory within the Institute of Tibet Plateau, we have developed a so-called Tibet Plateau climate system model led by Professor Yang Kong, just recently published on Science Bulletin. There are many of, for example, land surface parameterization and complex terrain modeling. We are moving fastly to the next step, so-called Tibet Plateau Earth Surface System Model, to integrate a cross-sphere process, hydrosphere, into this model. And the next step, we would very much want to integrate, for example, lithosphere, just, for example, introduced by Paul. He gave a very nice presentation. We have this kind of vision to integrate high-resolution lithosphere model with also human activities into this model. So eventually, we can have a so-called Tibet Plateau Earth System model. We also have planned recently to develop some kind of Tibet Plateau satellite. For example, develop a Tibet Plateau runoff and methane monitoring satellite to address high-precision optical SAR runoff measurement, hyperspectral methane detection, and multi-parameter inversion challenges, and all this data will be integrated into the Earth System model. Finally, just some proposal for the Tibet PlateauPlus. We do think TPDC can be used as a data platform to provide an open data platform for PlateauPlus to support data, for example, data storing, data archiving, exchange, and application. And provide data resources for compile valuable data from in situ remote sensing and other resources for global plateaus where data is sparse, and to develop data products for high quality, high resolution, systematically to investigate the modeling global plateaus, and also use big data analytics, use AI method to support and promote the big data research paradigm toward Earth system size of plateaus. This is our vision. So thank you so much. Again, you can encourage you to download and share your data at TPDC. Thank you very much.
Okay, thank you very much for that talk. We're now going to move on seamlessly into the second part of the session 3 presentations. And to start with, whoops, I've got to put my glasses on. We've got Professor Dai talking about early Cenozoic tectonic uplift and paleoclimate change.
Okay, morning, everybody. It's my pleasure to be here to report our workers about Lost Tibet Plateau. Our workers focus on the stratigraphy and tectonic uplift and paleoclimate change. Actually, this is our worker. It's about maybe 50 years, something. Okay. Yes. Sorry. This. Yes. Thank you. Okay. As we know, the Tibet Plateau is very important about everything. Right now, we study from the power about if there is a Tibetan or low Tibetan, and our workers just focus on the history about record. So this is the model. As we know, maybe the tenth of the model about how to Tibet platform and when Tibet platform, and how to influence the climate change and diversity. And this is a very new model about the Tibet Plateau. If we look, and we can see about the loss of the Tibetan, what's happened? It's I try to. No. Yes, and if we look back, yeah, okay. This here is a loss of the Tibetan. It looks like the sunless of Lost Tibet Plateau. Actually, there are many things took place in the Lost Tibetan, and okay, about when did the ascent of Lost Tibet Plateau? We have three opinions. Is one is a younger, is a middle mountain to Pliocene. This is very previously these years, and another is from the Oligocene, and another phase is Eocene. It's the early uplift from the Lost Tibet Plateau. Yes, and another phase is what climate conditions was is a Lost Tibet Plateau. So we firstly we did the integration about the stratigraphic age and to build up the stratigraphic age model, and then we discussed the tectonic uplift and climate change. So our worker focused on the Lost Tibet Plateau. Yes, and this year. We use the two hands. It's confused. Okay. Now, the data is the published data, and we integrate all of the data about the sedimentation and the magnetic stratigraphy, or the lethal stratigraphy, and the bar stratigraphy, and the proxies of the kilometer. And we did some new data from this and this. So we want to build up the stratigraphic successes and identify the uplift and climate change events in this region. So we firstly sort of the basis. Look, this is a basis about the 13 bases in the north of the Tibet Plateau, and the very big is like of the Chedai Basin and Longzhong Basin, and we classified this. This is out of the Tibet Plateau. The Donghuang and Hexi corridor. This basin belt, and then the Qilian Shan Basin groups, and then the Chedai Basin and West Qinling. So these three belts, the basic development history is different. And okay, so this is Jiuquan is out of the Tibet Plateau. We have a new stratigraphic system as the workers like we found the basement Liu Guzhuang. This is the older than the 14 million years. Then this is we have a new data about the Yumen formation. It's about 4.5 million years. And this is a new stratigraphic thesis. Then we move it to the east of the Heshi corridor. Is about the Wuvei Basin. This is a new idea about this basin. Maybe showed lots part of the Heshi corridor before the monsoon. And this is stratigraphy about the Wuvei, and we have a new data from the Lanzhou Basin, and then it doesn't work. Yeah, this is the Caidai Basin. As we know, there are two models about the Caidai Basin. One is older and another is younger. Our new data from the loss of Caidai would be suppose the older model, and then we get the stratigraphic thesis also Lost Tibet Plateau is about this. So we found there is a 4 sets of the strata. It's about early. It's about like this the data, and so let's move into the tectonic uplift. We found the basin initiation at about 55 million years ago, and there is a too early conformity at about 40 million years and 30 million years. Then two types of basin, rift basin and falleth basin in this region, and then yes, we use the sedimentation such as fissures and heavy minerals and provenance, and we conclude the uplift strength maybe start at the basic scale uplift since the 55 million. Then the two stages of the entire uplift at 42 million years ago, and the second is since the 22 million. This is maybe the mechanism is largely by the thrust, not other things here. And then we move into the change, climate change. This is we integrated the paramagnetic process of Lost Tibet. We found the climate condition generally is dry, but the wind at warm intervals interrupts the dry trade. And what else is more detailed? We found there is a green senses. This may be a wind at cold intervals in the dry trade. And this is a cold and wet intervals. It's about 1 million years. It's so long, a little bit so long. Another thing is we found the aridification is east of Lost Tibet. It's about 40 million years ago. And then we found a panel. This panel should be represents the moisture environment and the seasonal procedure. And we calculate about the MAP is about 40 or 80 millimeters. So in summary, it's about the 4 sets of the sediments, and then the stage, early Cenozoic is a 3-stage uplift, and then the something more detailed about the climate change. Okay, thank you very much.
Thanks, Professor Dai. So next speaker is Dr. Zhong Yuxiong from Institute of Tibetan Plateau Research. She's going to talk about the rise and demise of a central Tibetan Valley. Welcome.
Good morning, and my name is Zhong Yuxiong from the ITPCS, and thank you for the invitation of the BMKG and the PlateauPlus. It's a great honor to bring the paleo-elevation outcome of our group that focusing on the rise and the demise of the Central Tibetan Valley. As we know, the Tibetan Plateau, as the highest and the largest plateau of the world, has significantly influenced the Asian climate, the development of the Asian water tower, biodiversity, and the carbon cycles. But when and how this high elevation plateau has formed remains hotly debated, and many excellent scientists that are sitting here today has proposed many popular hypotheses. Professor Mark Harrison has proposed that the South Tibet rose to high elevation at 20 ma, and then the plateau formed at 8 ma. And Professor Andrew Smuch and the colleagues, as well as the Professor Paul Tapnier, proposed that the southern Tibet uplifted to high elevation during Eocene and then propagate northward. And Professor Chen Shanwang and the colleagues, Professor Jinggen Dai, proposed that actually there's a proto-plateau already exists since the 35 ma and then propagate and then grow outward. And Professor Linding and our colleagues proposed a slightly different hypothesis. We think that the Tibet, the orogenic belt in Tibet, especially the Ganges and the Central Watershed Mountains, rose first during the Eocene, and between the two mountains, there's a big valley system exists. So the paleo-elevation of this valley system between the two mountains is the key to solve the above scientific questions. And we further define this valley system as the Central Tibetan valleys. And these valley systems, including typical scenic basins within Tibetan Plateau, like the Jurza Basin in the west, and the Nima and the Lumpala Basin in the middle, and the Lachu and the Nolong Basin in the east. And we choose the Lumpala and the Nolong Basins as our researching focus. In the Lumpala Basin, located at the middle part of the Central Tibetan Valley, with a present average elevation of 4.6 kilometers, and the scenic strata, including the Niubao Formation and the Dingqing Formations. And based on the UPB dating results of the 9 layers of the volcanic tuffs that we find within the basin, as well as the seismic profiles, and we established a robust age framework of the Lumpala Basin, which constrains the Niubao Formation to 15 to 29 ma, and the Dingqing Formation from 29 to 20 ma. And then further based on the clump isotope temperatures, delta 14.7 temperatures of the lower and the upper Niubao Formation, as well as a collaboration with the colleagues at the University of Bristol, we developed a new approach, the Wet-Bob temperature lapse rate, to better constrain the paleo-elevation of the Lumpala Basin, and the results show that the Lumpala Basin was at a low elevation, 1.7 kilometers before 14 ma. And then the basin rose to over 4,000 meters by 29 ma. And our results at the Lumpala Basin testified the topography of the Tibet during 15 to 13 ma. There's actually 2 mountains sandwich the valley system in Tibet. And when the Lumpala Basin rose to 4,000 meters, and the paleotopography of Tibet become a high elevation plateau. And the Lorong Basin located at the east end of the Central Tibetan Valley with the present average elevation of 4 kilometers. And the scenic strata including the Bushu Formation, Meido Formation, and the Wahe Formations. And the Bushy Formation contains the Lucastrine Mars that could fit for the clump isotope analysis. And in the Meido Formation, we find this beautifully preserved and highly diversified leaf fossils that has 14 different morphotypes that totally meet the requirements of the clump isotope enthalpy paleo elevation analysis. And combine these two proxies, we revealed that the Lolong Basin was at 600 meters during the early Eocene and then rose to 2,900 meters by 14.4 MA. And further combine the paleo elevation results from the other basins within the valley. And we find actually the Central Tibetan Valley has experienced a westward rising process due to the successive detachment of the subducted Lhasa lithospheric mantles. And we further, in the past 13 years, and many paleo-elevation research has conducted within and around the Tibetan Plateau, and we summarized it, and it actually already revealed that the Tibetan Plateau has a very complicated rising histories. And Professor Dean and our colleagues further refined this complicated rising history as from narrow orogenic belt uplifting to high elevation plateau formation. In detail, we think that the Gandhis Mountain and the Central Watershed Mountain rose to over 4.5 kilometers before 14.5 MA. And the eastern Tibet mainly rose to over 3 kilometers by late Eocene. The Central Tibetan Valley rose synchronously with the eastern Tibet, but it has experienced the westward differential uplifting history. And the Himalaya mountains actually experienced the slow uplift process during the Paleogene times. And then during 20 to 17 MA, and it uplifted rapidly from 2 kilometers to near modern elevation. Actually, the rise of the northern Tibet, we still lack of the data, but we think the many episodes is during the Miocene times. And this complicated uplifting history of the Tibetan Plateau has significantly influenced the climate as well as the biodiversity of the Asia. And we further summarized it into 3 major stages. The first stage is during 16.5 to 14.5 MA, when the Tibetan Plateau posed as 2 mountains sandwiched lowland valley systems. The climate from the central Tibet to eastern Tibet and even the South China is very dry, and there's a big arid belt existed, controlled by the influence of the subtropical dry desert. And there's a wide distribution of the sand dunes. And the second stage during the uplifting of the eastern Tibet and the central Tibetan Valley, there's a unique Mediterranean-like climate emerged in the eastern Tibet and even in the central Tibetan Valley. And the Henduan Mountain became as a biodiversity hotspot since then. And the last stage is during the rise of the Himalaya and the northern Tibet. It is the final stage that the modern Tibetan topography has developed. And at this time, the South Asian monsoon and the East Asian monsoon stabilized to its modern shape. And vast forest emerged on the plateau and then disappeared, and the South China became humid and warm as the land of fish and rice. And here's the conclusion and the future perspectives. I'm not going to repeat the paleoelevation results here in detail, but I want to call that in the paleoelevation field, not only in the paleoelevation field, but in our field, we still lack of data. And we need more cooperation, not only within the Tibetan plateau, but in the other regions of the plateaus. That is the initiative of the PlateauPlus, and we also need more integration and the cross-validation with the modeling, and to better clarify and understand the linkage between tectonics, climate change, as well as the biodiversity. And that's all. Thank you for your listening.
Hey. So the last speaker of this morning is Dr. Muhammad Qasim. He's going to talk about the Western Himalaya uplift and erosion in Pakistan. Welcome.
Thank you very much. I'm thankful for Professor Ding to give me an opportunity to present our work on the Himalayas, about the Himalayan erosion. So today I'm going to talk about the detrital zircon UPB evidence for Western Himalayan uplift and erosion in Miocene foreland basin, Pakistan. So I'm working at the Sultan Qaboos University, Oman. Recently moved about 3 years ago. So this is a general tectonic map of the Himalayas, where to study the mountain uplift after the collision, we need to know about that how the Himalayan fault system has been developed over the time and providing the detritus to the evolving foreland basin. So generally, because we have classified the Himalayas into the 4 tectonostratigraphic zones from north to south, as the Tithian Himalayas, which is separated by the South Tibetan detachment system, and then we have the higher Himalayan zone, and then which is separated by main central thrust. Below that is the lesser Himalaya and the sub-Himalayas. Presently, the foreland basin along the Himalayan belt is mostly restricted to the sub-Himalayan zone. So we have only few outcrops in the lesser Himalayan zone, but in the Pakistan, this is the part where we have studied. So this yellow color represents all the foreland basin system along the entire Himalayan range. And this is the northernmost exposure of the Himalayan foreland basin, which is now present in the Miocene foreland basin. So our study sections are located here. One is the Balakot, and then we have some Muzaffarabad section here, and then we have the Murray section. So the importance of this section to study for the detrital zircon evidence is that because these are the oldest continental deposits which are exposed in the northwestern Himalaya. So this will provide a better constraints about how the mountain belt evolved after the collision. So today I will discuss briefly about the provenance changes or using the detrital zircon signatures, and then their tectonic implications, that how we can link the provenance changes or the tracing their sources and link them with the uplift of the different mountain, tectonic blocks in the Himalayan mountain system. So these are the study map, geological map of the study area. We collected the samples all along this belt because these Miocene foreland basin systems are complexly folded, and it is difficult to constrain their younger sediments because there are several faults. So what we did, we did the structural mapping along this belt to collect our samples from the cores of the anticlines and the core of the synclines, so that we have a variation from the base from the very oldest sediments of the Miocene foreland basin and the youngest one. By doing this, we can see a complete spectrum that how the sedimentary pattern has been changed in the Miocene foreland basin. So this is a journal like the samples which we have collected from, which represent some lower parts, some from the middle part, and some from the uppermost part. So these dots represents the sampling localities, and these are some field photographs that how these clays look like in the field in the area. This is the second geological map of the Muzaffarabad region that we have collected. This is a continuous sequence, and here we collected all these samples from the Miocene foreland basin, and this is the third section where we started to get the samples from the base to the top. So then we compare all these sedimentary provenance in the Himalayas, not only within the western Himalayas, but we compared our results all along the Himalayas from the India, Nepal, Tibet, and towards the eastern Himalayan syntaxal area. So these are some petrographic observations that we have did some traditional petrography to study the clast and their composition, and then we use the previously published studies to compare that where we have our petrographic signatures, and then we link these petrographic signatures and the tectonic discrimination plot to differentiate about the different source of the sediments, their tectonic regimes, and then we linked and together with the detrital zircon signature to uplift mechanisms. So these are the results from one section from the northwestern Himalaya, and this has been published in the 2025 in International Geology Review. We have published this data. So we have a very typical patterns that we have the 5,000 to 1,000 million years, and this is very consistent. But another is that we have a younger pattern, but the younger pattern, as we go up in the younger samples, the percentage of the younger detrital zircon decreased. So that means we still have some barriers that which restrict the derivation from the younger sources, which is the Kohistan Ladakh arc or the Karakoram block, to provide the detritus to the evolving foreland basin. And then we compared this our data from the study area, this Murray Formation, with the Dakshai Formation from the India and from Dumri Formation in the Nepal, and then the Barer Formation from the Bengal Basin. So we compared and our results and compared that how is the similarity along this 2,400 kilometer long Himalayan belt. And by comparing that, our most of the detrital signatures there represents the Tithian Himalayas and higher Himalayas. But particularly in the northwestern Himalayas, that we have some signature from the lesser Himalaya which has not been previously identified. And to constrain this, we have compared statistically our data, because this is just a similarity between the edges. To quantify by quantitative analysis, we run the MDS plot to compare which source is most likely related with what is the similarity between the sediments. So what we found there by these statistical analysis, that most of the samples from the northwestern Himalaya and the eastern Himalaya, they share the similar signatures of the detrital zircons. But in the central Himalaya, in Nepal area, their signature is different, because they are mostly derived from higher Himalaya and the Tithian Himalayas. But in the western and the easternmost segment, they share the similar detritus. And these thorium and uranium ratio plots, which we use to constrain that our zircons are mostly, because this ratio is used to differentiate between the igneous and metamorphic zircons. So most of the zircons, they are from igneous rock in the 500 to 1,000 million years range. So based on these provenance results, then we constrained about, we developed this tectonic model that we have constrained from our previous studies, that the Himalayan foreland basin, the collision started in the northwestern Himalayas about 55 million years. And this we constrained by the detritus signature, and we do have the edges for those units by the volcanic ashes. Once the basin has been developed, that we receive the detritus from the Kohistan, the Ahar. So there is a controversy about the edges of these different fault systems, because MMT has been dated at 55 million years, and the MCT has been dated about 25 million years in the central Himalaya, but in the Pakistan we have the several faults which are equivalent to the main central thrust. So what we did, the age of this fault, Balakot fault, which is considered to be equivalent of the main central thrust, has an age of about 44 million years based on the high pressure eclogite along this fault zone. The Punjab thrust, which is basically located within the lesser Himalayas, this age of this fault has not been constrained, but a fault south to the Punjab thrust has been constrained about 8 million years. So based on our detritus zircon signature, we thought that this Punjab thrust was an active between 25 million years, between 30 to 25 million years. But recently in 2025, a paper has been published about the age dated from a German university that has constrained the age about 30 to 24 million years, so which is perfectly aligned with our interpretation. So we got that during the deposition of this Murray formation, what we have received, the detritus zircon signature, that this terrain was, at least the part of the lesser Himalaya was already uplifted, which provide the detritus to the Miocene foreland basin. So before that, the people thought that only the MCT was active when the deposition of the Miocene foreland occurred. Another interesting result is that we have the similarity between the signature when we compared along the strike. So we thought that detritus, because the Indus river system and the Brahmaputra river system, they are draining from the similar tectonic trends. So they are bringing the similar detritus to the evolving foreland basin. While in central Himalaya, the Ganges, the Ganga river system, that is draining just immediately south of the MMT, and that is why they do not have some younger signatures in the Nepal Himalaya. That is the difference in the provenance sources. So these are the just conclusions. I don't want to repeat. Thank you very much. If you have some questions, you may ask.
Okay, so let's move on to the discussion section. We have like 10 to 15 minutes for the previous 4 speakers. There are any questions? Anybody else? Okay.
My question for Dr. Xiong Zhongyi. I like your talk. You talk about the Central Valley. I think it is very correct. But my question is, probably beyond your talk. My question is, when the Central Valley began? Maybe Cretaceous, maybe Cenozoic. How about Cretaceous?
Yeah,
what do you think?
That is beyond my talk, but I will try to answer your questions. What we think, when the Ganges mountain and the central watershed mountain began to uplifted, and we think that this valley system already existed. So probably will be like during the Cretaceous time or earlier. And as I've heard your group's talk about the suturing of the Bangong-Nujiang suture zones. From the paleoelevation data, when the Ganges mountains rise is like during the Cretaceous times. And the northern part, the central Tibetan, the central watershed mountains, and the thermochronology data shows that it also like uplift during the later Cretaceous and the early Cenozoic times. And what I think is that during the later Cretaceous to early Cenozoic, this valley system already exists. Thank you.
Okay, thank you.
Also for Dr. Zhang Yu. You know, you talk about the uplift of the Gangdesi batholith. I think we're far enough along that we can be, you know, more sophisticated than treating it as a single object that pops up, you know, at in the late Cretaceous, because it's pretty clear that granite Plutonism was going on, you know, from basically late Jurassic all through the Cretaceous. But it's also clear that, you know, southern Tibet and a block, you say south of Lhasa, that remained thin right up until the collision began. Okay? So, you know, putting on the graph Gangdesi batholith, I think ignores the sophistication we've got to, which is we recognize that, in fact, the body of the batholith, the central portion of the Gangdesi, was certainly, there was a high stand there. It has been probably since the late Jurassic. But in fact, it wasn't a single rectangular blob that came up like this, that it had a tapered form to it, right up until collision.
Thank you. I'm very appreciative for Professor Mark Harrison's explanation for me. So you mean that the foreland basin systems of the Gang during the subductions. Thank you. Thank you.
My question is to Professor Jin Lee about the data center. I just had a quick look to your website, and I wonder if there is any way of getting structured data. I mean, for instance, if I want to know where are the place which has been done sampling and dating and so on, is there any way of getting such kind of data from your data center?
You mean, excuse me? Do you mean the access to the website? You try to...
Yeah, I tried to get information for a subject, but it's referring to publication, not to structured data. I mean, there is no single file for a specific kind of data.
Okay, I'm not very much sure. You mean you cannot access to the website of TPDC?
No, I did. I could access your website,
okay.
But for example, if I want to know where are the Jurassic rocks or something like that,
okay,
how can I?
Search box. You can just put the keyword into the search box, and you can get your search results.
That's what I did.
From there, you can download from each. For each data, we do have metadata to describe the data in both Chinese and English. And there is also downloader. For example, link to the downloader. If you click the link, you can download data. Right. And if you click, for example, the data also, and this link will link you to the other data products produced by this author. I think there are quite some links in the website. Okay. Maybe we can check together during the lunch break.
Okay, thank you very much.
If any problem, you can provide feedback to, for example, to the techniques within TPDC where we can try to improve.
Thank you.
Yeah, there are detailed metadata for each data set.
Thank you. My name is Jaya from BMKG. So after I follow the presentation from the Professor Zhuang Dai and Dr. Zhong Yu Xiong and Dr. Muhammad Qasim, you are explained about generally the effect of the Indians collision to the erosions from the Himalaya Tibetan plateau, and In so one region is uplift and the other region is palay, and then uplift and palay. My questions, do you have the web length, buckling web lengths? Do you have the web length of the lithosphere buckling, effect of the collision Indians and the Eurasian continent? If you have the data of the web length of buckling of lithosphere, what the implication the buckling phenomena for the seismogenic? Thank you.
Sorry. Okay, maybe I can get your message, but guess about what is your question is how and Himalaya as a canadian zone affects loss effect, and
Everybody's having trouble hearing.
Sorry. The one of the effect of the collision between the Indian continent and then the Eurasian continent, in the some region is the uplift and the other region is palay. You understand?
so about the uplift, what causes the uplift?
The uplift.
Uplift.
Yeah, uplift and palay. Okay.
我这个
Jelas itu.
Okay, question is about collider and topography and the difference in high mountains and the basin, low basins.
Yes,
And,
so my explanation is the collision between the Indian continent and the Eurasian continent is from the buckling of the lithosphere. Buckling.
Okay. Yes, this is a very interesting, and we try to do it, but at the how clear to make the uplift and the effect and loss or something.
Yes, I want to answer your question about the collision and the buckling. Yes. Definitely by the load of this, when India collided with the Asia, that we have the Khoistan Ladakh arc, so we have a flexure slip, the basin has been developed. So when the basin is developed, because this is a continent to continent collision and the Himalayas are getting rise. Before the collision, we have the most of the drainage system that was from south to the north. But when collision occurred, because the Himalayan mountain was started to rise, and then the drainage system was established, new drainage system was established from the north to the south. And that brings detritus to, because in the mountain front we have the ocean, and that ocean has been consumed, and then we have transition from the oceanic environment to the continental transition, that the river system has been developed. That brings the detritus from the uplifting of the mountain belt, and then because the Indian plate is continuously goes down underneath the Eurasian plate, that give rise to the Himalaya.
Okay, so my question is how long the buckling web length? How long?
The time?
How long the web length of the buckling? How long?
Yes,
the distance.
The width, that could be about 200 kilometers, because we have the, from the west to the east, we have the different topography, because in the western part, we have the salts in the subsurface, so there we have a very broader fold and thrust belt, about 300 kilometers or 400 kilometers, but as we go into the central Himalaya, there we do not have the salt. That will provide a narrow fold and thrust belt and high elevation. So Generally, it varies from 100 to the 300 kilometer.
Okay. And the third question is, what is the seismogenic implication?
Seismic?
Seismic.
Yeah, the seismic we have in the northwestern Himalaya, we have a seismogenic zone that we have the continuous earthquake. So that is an active seismicity still there along the syntaxial band. So we have the frequent large earthquake along this area in the foreland basin because we still have a continuous deformation.
Okay, thank you.
Okay, thank you. I think Professor Lee would like to have another comment.
So, my dear colleague, I just want to clarify how to search data at TPDC. I just also tried on my cell phone. On the right upright corner of the website, you can find the icon called Found Data. And for example, you just type in Tibet. You can find 2,318 data set with this keyword in the metadata. And you can also rank the data in terms of view times, in terms of download times. And then you can get access to that data set. It's just one example. Thank you very much. I just double checked on myself.
I have a question. I have a question for you too. In that, obviously, the climate models that we use are global. Are you happy to have global data, even though your project or your database is for Tibet? Or
we do like to archive and also to have global data set within the TPDC, and we do share some global data set. Already we shared some global data sets. For example, permafrost. Thank you very much.
any more questions?
I actually have one question for Zhongyu. Right here. So you mentioned in your talk the climate in eastern Tibet was like a Mediterranean in Eocene. What evidence is it based on? Thanks.
The Mediterranean-like climate in eastern Tibet, we have two lines of evidence. One is that we find the typical leaf fossils that exist in the Eocene Lucastrine strata within the Tibetan plateau that are similar in the modern Mediterranean climate, Mediterranean vegetation. And we also, like a collaboration with our colleagues at the University of Bristol, Paul and Alex, and the modeling results show that the precipitation in eastern Tibet posed at there's like two peaks during the spring and the late autumn, while the summer is dry. And so we think this is like similar with actually in the Central Asia, the Mediterranean-like climate. So that's we think at this time there's a climate that like the modern Mediterranean climate in eastern Tibet.
Okay, that's the bell for saying the questions are all done. Has anybody got any final quick question? In which case, I think we should call this session to a close and thank the speakers again for some fascinating talks.
Thank you very much. That is the end of the morning session today. Thank you for the speakers and the chairman. Before we step to the next agenda, I would like to inform for all foreign guests that we will visit our multi-hazard early warning system room right before the lunch. And then now we are heading to the next agenda, the handover awarding souvenir, token of appreciation for the keynote speaker, Professor Paul G. Valdez, Professor Erwin Apple, and Professor Sin Lee. We invite the Director of Earthquake and Tsunami, Dr. Daryono, to give the token to the mentioned speakers. All right. The professor is Professor Paul G. Valdez, Professor Erwin Apple, and Professor Sinley. Okay, give applause for the mentioned speaker, please. Same way. And for the last speakers. Thank you very much, Dr. Daryono, and please be seated. Okay, now I would like to ask some help from our college and the committee to lead the way to multi-hazard early warning system room for all of our foreign guests. Please, and for the participant, for the rest of participant, we're still waiting for the lunch after this. Thank you so much, and thank you. For all participants, you can enjoy the lunch after this. The computer will tell you where is the place you can take the lunch.
Check, check. Dear participants and speakers, please gather in the auditorium room immediately because we would like to start the next session immediately as well. Thank you.
So if that just forward, that's back.
Yeah, I hope now the battery is better during my talk. No?
Yeah, not on it.
They will have to set up.
They put it on, yeah.
So please come in. We should start very soon. And after the discussion, you take over. Okay. So welcome to this first afternoon session, the session 4 now on paleoclimatology, paleontology, and evolution. And I want, we do it as before. No? After the first 4 talks, there will be a discussion on all these 4 presentations. And now the first talk is Alex Farnsworth. Please, it's your stage.
Great, thank you. It's wonderful to be here, and I thank the organisers of PlateauPlus for their invitation, and very much as well for BMKG for hosting this event, and Indonesia. It's been actually lovely to be here and meet everyone. Or we might be waiting a little bit. Aha. Great, thank you. So I'd just like to put a very warm welcome to all of my valued kind of collaborators on this project. It's been a long time in making this project, and it pretty much incorporates the last 10 so years of a lot of our work here. So, go ahead. So when we think about the Asian monsoon, it has a huge and long history of research. Over 60 to 70 years, people have been trying to investigate exactly how old is the Asian monsoon and when did it instigate. You know, right from the early 70s and 60s, lots of work had gone into looking at the sort of Quaternion, Pliocene time periods, and it was really only generally thought that the Asian monsoon was maybe at most 3 million years ago. And it was kind of interrelated to what our kind of thoughts and feelings, again, what the Tibetan plateau was doing again at the time period, how old it was. But as we kind of went through the decades, as we started to better understand the geology and the interactions of topography and meteorology, we started to really start pushing back our understanding with new discoveries of exactly when the Asian monsoon kind of was first formed. And that went all the way from the early to mid-Miocene, later to the late Miocene, and today as early as the mid-Eocene. Most people generally accept that there was a monsoon of some form in the Asian region. And again, even as far back as the Cretaceous, there has been some prediction that monsoons were present and could have formed in these time periods.
So the real question is, okay, if monsoons have existed in Asia for a long, long time, what type of monsoon was it? Monsoons are not all the same thing. They have many different driving mechanisms, all create different ideas and dynamics of what drives a monsoon, and that can change through time as well. So if we start thinking about in the different types of paleogeographies where we can really understand what this long-term evolution of the Asian monsoon is, let's see if it will go forward. There we go. So this animation shows a nice reconstruction of 3 different paleogeographies that run through time, in this case all the way from the beginning of the Cretaceous to the modern day. And what you can really see is, by general eye, they're all doing the exact same thing. The land-sea distribution is fairly similar, but by eye what you can really see is the topography used in these reconstructions varies significantly, not just between time, but between all these different reconstructions. And this idea is certainly going to have a big impact on what the monsoon was doing. If we take a little look at one time period, just to have a focus in on what's going on, let's see if this pointer, there we go, and just take it the Danube. Again, just very briefly, you can see, especially in this sort of GTEC orography, very, very high, especially in the Asian region. But when we compare that to the Scotese or this Robertson's reconstruction, they have much lower ideas of what the topography was like. Bathymetry, on average, is pretty similar. The land-sea mass is, again, on average, similar. I picked this time period because it was the most different, and it was really what they express as the sea level at the time where you get this difference in the land-sea mass itself. Now, the good thing is, in Model World, I can put these 3 different reconstructions into my model to have a look exactly what they would predict was monsoonal or not monsoonal at these times. And if we take a very brief view of it, they both all tend to agree in the early Cretaceous there were potential monsoon systems developed in the Asian region itself. But by the mid-Cretaceous, all 3 of them tend to say there was a drying. By the early Cenozoic, a kind of transitional phase. Some of the paleogeographies like GTEC suggest there was a monsoon starting off. Some like Robertson's and Scotese suggest not yet. And by the sort of mid-Eocene to the Neogene, you both see all 3 start to converge again in saying that in Asia, monsoon conditions were present. Now, this is all generally the long-term trend, and what this gives us an inference is the long-term trend in the monsoon is actually not really just about orography. It is about this land-sea distribution that potentially sets the long-term evolution side of that as a baseline. And what the orography is doing, as you can see with the different heights and these different models giving different time periods of evolution, what they do is they enhance the monsoon. They allow it to become much more intensified and invigorated, both spatially and in magnitude. Now, of course, what we really care about here is the actual data. What does the data say about what the monsoon is doing? And this is where our colleagues at ITP, especially Dr. Zhongyu Zhong, have spent a huge painstaking amount of time to reconstruct these 4 different time periods of what these different hydrological proxies suggested was the type of monsoon type of climate here. And again, you can see in broad sense in the southern latitudes in the late Cretaceous to mid-Eocene, potentially monsoonal, as well as some of the high latitude coastal regions, but this big dry belt existed throughout most of the sort of Asian region there. And again, that starts to disappear as you go into the late Eocene, you start seeing a bit of push. India stays very dry, and then by the Oligocene, you see what is a much more modern day expression of what we see as the monsoon domain, the area that would be monsoonal. But of course, with these types of proxies, you can't really tell exactly what might be driving these signals and exactly how strong that monsoon might be. But what we do know is all those paleogeographies we showed initially in these 3 different reconstructions, they're wrong. They use very different ideas of what Tibet looked like in the past. Of course, in the last 10 years, especially the work that Professor Ling Ding's been doing and our other colleagues in ITP and Chengdu and Zishuanbana, is trying to come up with a new idea of exactly how this evolution of the Tibetan plateau was, from the, say, the Lutetian and the mid-Eocene all the way to the modern day. And if we look at the sort of hydrological response as we get this sort of central Tibetan valley elevating, and as well as the eastern portion of the plateau elevating, what you can generally see from the precipitation signal, there we go, is we still have this very dry valley that persists all the way out to the edge of China. And again, most of northern India and greater India is still very dry at this point. Southern India and parts of Southeast Asia and some of the coastal regions are wet. So they're still saying there are these sort of quite summer-dominated rainfall signals coming into that. But as we start stepping through into the sort of mid to late Eocene, you start to see this persistent increase in rainfall in the Asian domain, but not in northern India at this time. It's only once we get to into the Chattian that we really see the sort of monsoon signal really kicking off and looking a lot more like the modern day signal itself. If we start looking at what we say is actual monsoon, so we use a monsoon index that determines is that a monsoon precipitation signal or not, again, you can see this similar signal. Very dry central areas of the Asian region and India, but it's only once you get into the Chattian do you really see that sort of monsoon domain kicking in and suggesting it's a lot like a modern day expression of a monsoon. And again, we can use other expressions of what a monsoon is determined, such as the as a monsoon precipitation index, or just the seasonal distribution again. All these sort of different types of diagnostics to try and understand what that monsoon is. So the real question is what's driving it? Here we have three different sorts of models that might be working in this area. Again, we have our Booz and Quan, where you just need the Himalaya or a strong orographic front to drive this moist subcloud entropy. You have this heat pump idea where Tibet is acting as a big pressure cooker, pumping up energy into the atmosphere and setting up a monsoon type of circulatory pattern. Or we have this sort of general tropical size where the intertropical zone of convergence is going north and south over the equator. So when we start looking at what the ITC monsoon is it a ITCZ? No. What we see is both in the Indian region and the East Asian region, when we apply these sort of diagnostics to look at the location of the ITCZ, it plays pretty persistently around 10 to 15 degrees of latitude in both domains. And what you really see, this area of high convergence that starts to develop by the Oligocene and the Chattian in this case, in both India and East Asia, is really being driven by non-tropical convergence metrics, not eddy-driven, but this angular momentum-driven type of momentum, bringing in much moist, wet conditions. If we look at this sort of subcloud entropy, again, this is the Booz and Kwong. If you just had this topographic barrier, you should see a very strong kind of signal that you see in the modern day and Oligocene. But we don't see it when we just have a high Ganges. There is no sort of insulating effect from the Ganges that drives this sort of Indian monsoon. Again, it's only by the time we get to the Chattian that this develops. So if we start thinking about the heat pump itself, all we're showing here is in the mid-troposphere, there's this big, big heating effect of the Tibetan plateau, this big anomalous heating centered over the plateau. And when we look over the season here from January to December, what we care about here is just this black line. When this black line is present, it shows there's a very strong heating effect of Tibet. Now, if we go back through time, again, what we can see between the mid-troposphere and upper troposphere, this doesn't exist, and it only starts to develop in a small way from the Parktonian, the Pre-Ebonian, and the Chattian. So it looks like it's, again, the Chattian realization of what the monsoon is. Now, was Booz and Kwong wrong? That's the real question here. We can run the exact same experiments, in this case about 20 different experiments of different orographies through the modern day to see. And what we get in a very quick generalized sense is, in both cases, when we just have a ring of mountains, no plateau, we get a very similar dynamic aspect of what the monsoon looks like. So Booz and Kwong is certainly right. Our model agrees with that. If we move very, very quickly into a Lutetian type, this dual mountain Gandhiji, again, the modern suggests that the monsoon system, as it is in the modern, is again very similar. So there's a disconnect here between what Booz and Kwong said in the Lutetian when we have this dual mountain, there was a no monsoon. In the modern, when we have a dual mountain system, there is a monsoon. So there's more going on than just having this high mountain range thermally insulating the monsoon and creating and driving it. It looks like it's really being driven by this heat pump effect in Tibet itself, this sort of angular momentum-driven system that's pushing that moist, high-entropy air further north. And with that, I'll leave it there. Thank you.
Yeah, thank you, Alex. The next speaker is Chunjung Nie.
Okay, thanks for the opportunity to talk about some of the research from our group. This is in, mostly my postdoc Shibao Gao's work, but it's in collaboration with a few colleagues, including Alex Pullen and Shufeng Yang from Zhejiang University. So the title is "The Early Pliocene Warming Drove Rapid Northern Tibetan Erosion and Taklamakan Desertification." So for some background, so as we all know that river incision and the desert formation has been widely used as evidence for Tibetan uplift in Asia. But recently more and more work shows that there's a quite long delay between uplift and the river incision. And there's involved pretty complex surface processes. So what about the desert formation? There's some very solid evidence suggesting the Taklamakan Desert formed around 5 million years, as you can see from the lower right corner, the figure. The Taklamakan Desert was an episodic lake before 5 million years, which changed to alternation between aeolian sand dune and fluvial deposit. And in terms of the reason, people think maybe that indicate northern Tibetan uplift. But if you ask tectonics expert, maybe many of the experts will now think the northern Tibet experiencing significant uplift at 5 million years. So there's a long delay. So we think around 5 million years, climate changed dramatically. It's a late Miocene Pliocene boundary. So we asked whether this formation or desertification is related to this global climate shift. That's our hypothesis. So this figure shows the sea surface temperature from different latitude, and we can see around 6 million years sea surface temperature dropped to below the pre-industrial value. And then followed by rapid warming. So there's some evidence, many evidence actually suggests the glacier developed in different part of the continent. Then with the warming, then the glacier melting will produce a large amount of water, a high flux of water, which can cause very quick erosion. So if we look at the low temperature summer chronology data, you can see the yellow symbol represent close to 5 million years ages. And these ages are all near the modern glaciers. However, to produce a desert, you need a large amount of exhumation. However, the amplitude of incision or exhumation is unclear. So to study the amplitude, we sample a granite altitude sample from this small area, and which is right north to the modern northwest of the modern glaciers. And the result are very consistently shows there's a 1 kilometer exhumation around 5 and 4 million years. And we also ran some model simulation, suggests the climate was very dry in this time period, and there's no way the precipitation itself can produce 1 kilometer exhumation. If we notice the current altitude transition is 45 kilometer offset to the modern glaciers outlet, and using the modern 10 millimeter per year slip rate, if we calculate back, we get a 45 kilometer offset. So that means that this, so the sample set back to 4.5 million years was right here, and it's directly downstream of glacier.
So that's, we think this 1 kilometer exhumation produces a large amount of loose sediment for desert formation. That's, I think it supports our hypothesis. So if this is correct, we should be able to see some changes in the downwind Chinese Lost Plateau, because when there's a large desert form, the loose sediment will be able to be transported to the downwind Lost Plateau. And you can see from detrital zircon data on the Lost Plateau, 8 million years, the loss is pretty far from West Kunlun and the Pamir mountains. But near 5 million years, they shift to be consistent with the West Kunlun and Pamir source. So this is one indirect evidence supporting our hypothesis. So then we also compare with the South American aeolian system, which also have a late Miocene age. So the Lost Plateau here, it formed around 7 million years, a major part. And this part also have a late Miocene age. And we think maybe out of this aeolian landform, their formation is related not to the uplift, directly not to the uplift, but instead from this climate, late Miocene climate cooling and formed by this warming. So the general implications, so as we all know, with global warming, glacier melting, the hazard and erosion increase, which cause destroy the damming and decrease the water power's life. But the long-term effect, I think, has been unknown. Using past as a key to the future, we think we like to argue that climate warming-driven glacier melting result in if this goes on, will result in river incision and we can result in a desertification. That's something that has not been paid attention to incorporate in the models. So with that, I'd like to thank you for the time.
Yeah, thank you, Junjang, for keeping the time. We saved some 2 minutes now. And next speaker is Tao Dang.
Good afternoon for everyone. I'm very happy to this chance to share our recent studies about the Mammalian fossils and their relationship with the upper left of Tibetan Plateau. Waiting a second. Okay, my title is Upper Left of Tibetan Plateau, contributed to the northern China and the Central Asia becoming the center of mammalia evolution. We know the India-Asian collision was one of the most important orogenic events of the last 500 million years ago, which not only greatly changes the topography and the climate in Asia, and more widely, but also strongly influence the evolution of the biosphere. So, why? For example, we give in the Oligocene, we can find the giant rhino. Its body size can reach the 24 tons, maybe equal to 4 the modern Africa elephant, the whole the body weight. But we can find in the south side of the Tibetan Plateau, we can find a locality with the Giant Rhino in Pakistan, the Siwanik area. And the most locality of Giant Rhino is the north side of the Tibetan Plateau. So we guess, at least in Oligocene, in the Tibetan Plateau, there is a central valley. So the largest land mammal can reach from north side to south side and go back to north side from the Pakistan and the India subcontinent. And the significant change just between the Oligocene and the Miocene, the boundary. Before this boundary, maybe before the 20 million years ago, the Tibet, the biota, including so many tropical and tropical, subtropical forms. After the boundary, there is no any tropical elements. We can find, for example, the fish include slow carps is a typical type, the Tibetan, the modern fish, and live in the cold waters. And because the Tibetan Plateau with very high elevations, so the warm and humid air can't reach the Central Asia. So we first time to find the bovine in a lot of the sheep and ox. The first time they have the primitive horn. Why? Because in the very dry elements, the male individuals must fight for their territories. We have another example. For example, the very old or the primitive giraffe also appear in the north part of Tibetan Plateau in Xinjiang and Junggar basins. Also, the male, the giraffe, with it's a single horn to fight for territories. For example, if there is a forest environment, the male don't need to fight for the territory, for the plant, the source. But in the very dry area, the male must fight for its population to occupy territories. And until to the late Miocene, all the Central Asia, including the northwest of China, became the very open, the grassland, and very dry. So we can find so many members of riparian fauna. It means the solitoid horse, the faunas, they occupied all the northern part of the Eurasia. So the area became the very dry areas. And we can find, and the modern, the savanna biota or the savanna fauna in the Africa is a very dry environment. But only few forms, for example, hippo and elephant, can trace back to the origin in the Africa in situ. But most forms, only 7 million years ago, they live in the Africa. And the 10 million years ago, these forms origin in northern parts of the Tibetan Plateau. Because the upper left, the Tibetan Plateau, make this area become very, very dry. Then these forms, they migrated to the Africa. And we can find in the Pliocene, the Tibetan Plateau, for example, the antelope, the Tibetan antelope origin in the Tibetan Plateau, and we can find more cold the cold adaptive the fauna in the Tibetan Plateau, especially, for example, the uni rhino in the Pliocene, about 5 million years ago, the megafauna, the Ice Age megafauna arranging in the Tibetan Plateau, because in that time, including the Himalaya mountains, the rich in modern the elevations, the all of area became the cryosphere, became the Ice Age world. So we give the more examples. For example, the slow leopard, about the 6 million years ago, arranging in the Tibetan Plateau. In the Pleistocene, in the Quaternary, this cold adaptive forms, they expand their distribution in the northern part of Eurasia, the Turai, Africa, Southeast, maybe including Indonesia, this area, and across the Bering Strait or the Bering Land Bridge, they reach North America, and across the Palama, the bridge reach the South America. And we can find the ship and also arranged in the Tibetan Plateau, and westwards the migration, and eastwards migration across the Bering Strait, or it means the Bering Land Bridge. For example, in Alaska, the bighorn, the white bighorn and the Canadian bighorn, all arranging from the Tibetan, the plateau, and the Arctic fox, or the lynx in the bobcat in the Canada, also arranged from the Tibetan Plateau, from the northeast corner, at least 2 times from Tibetan Plateau reach the Canada. So, sorry. And the Arctic fox also arranging from the Tibetan Plateau. And from this picture, we can know in the Eocene, along the central valley of the Tibetan Plateau, in the east part, we can find so many tropical plants, for example, the banyan tree, and some mammals, for example, amphibian, the rhinoceros, Amynodon, and the Brontosaurus live the east part in the central valley. And the Oligocene, we can find the palm tree and the giant rhino, and so many the tropical fish. And from Miocene reach the 3,000 meters elevation, and the Pliocene reach the modern elevation, became the arranging of the megafaunas. And last, use this picture, we find the dispersion from Tibetan Plateau at least 3 times, and the 20 million years ago and 11 million years ago, the last time in the 5 million years ago. Okay, thank you.
Thank you, Tao, for the talk. And the last speaker now, before the break in the discussion, is Jingen Dai.
Okay, I'm Jingen Dai from China University of Geoscience. First of all, I would like to thank Professor Dean for this invitation. And it's really a pleasure to be here in Indonesia. And I really appreciate the warm hospitality from the colleagues of BMKG. Actually, my previous study focused on the uplift Tibetan Plateau and the Himalayas, but today I will shift my perspective to the consequence, how the topography goes infect the climate and also the ecosystems. So can we go back one? Okay, thank you. One very simple but very powerful or didn't change my purport. One really good, simple, but powerful message is that we compare to the related abundance about the C4 and the C3 plants, because C3 plants usually efficient in cool, moist, and shade environments, while C4 plants adapt to hot, dry, and highlight environments. For the parallel environment reconstruction, we rely on the plant wax like this and biomass, especially for this data 13 carbon, because C3 plants usually deplete in this value data 13, while for the C4 plants, they are much more enriched. So based on this, we can distinguish globally, the C4 plants appeared during as early as late Oligocene to Miocene, but it expanded during 8 to 4 MA. And the modern results show that the low CO2 level acted as a global trigger. You can see here, when the CO2 level is about 217 ppm, so this C4 plants, you can see they distributed both in tropic and subtropic area. But even with the same CO2 level, you can see that the origin of the C4 plants is different. It first occurred in Northwest Africa, but the latest in occurrence in Southeast China. So there are some other hypotheses proposed that said that maybe monsoon intensified. But except for the CO2 level and also monsoon, there are also other factors that influence the climate, such as the temperature. And so, as this morning by Paul, you can see that actually this local climate will shaped by the topography. So the most repeated change in topography evolution is from South Tibet and the Himalaya. And here there are many studies focused on the Western Shivalika Basin, and for the eastern and central, and especially for the hinterland, there are very limited study. So this will hand in for our understanding the full C4 expansion patterns. Actually, in the hinterland of Himalaya, there are several Miocene basins, such as the Zada and the Jilong, and also Dati basins. These basins are full of tertiary later Miocene sediments, so it's ideal place for the ecosystem reconstruction. Today, we will focus on the Dati basin. This basin actually is located in the, actually here is Mount Everest and the Xixiabaoma. So it is kind of in the land-shared area of this organized value. And also here, there are a lot of sediments which are well dated by the manual stratigraphy. So we collect 34 milestone samples. We analyzed about the biomarkers and the GDGTs for the vegetable and temperature reconstruction. Here is the results about the distribution of the N acorns. You can see that they are really high constant about the long chain N acorns. And also this shall present really strong or even carbon-carbon prevalence. and high CPO values. So this evidence shows really clearly that they record terrace high plant origin and represent the information of regional vegetation. So this most important figures didn't show up. So, we can see from this date, this task, you can see actually we have two stages. The first stage, they have very low, they have a deep data 13 values, which means that the percent of C4 plants is very limited. And the second stage is shifted to about, we calculate the percent is about 27% C4 plants. So it can represent that the large expansion, C4 expansion. And when we go back a little bit, we find that the early C4 arrived at 8.3. So this is much earlier than this results from the farmland and also the ocean results. Hopefully we can see. Oh, I don't know why. I don't know why, yeah. But you can see here, actually here is the results about the carbon isotope. And also we conduct about the hydrogen analysis. You can see the hydrogen analysis have about 6% variation. It means, so it is really correlated with other from ocean island and Shuai Island. It means that the South Asian monsoon stronger flukes length. And also we based on the GDGT to calculate the soil and the air temperature and also the salinity. Here actually this is normal one. You can see this the results about the carbon isotope, and so they didn't show any coordinate with about salinity, also soil temperature. You can see this change repeatedly, but don't show any change. So it's not related to our this carbonate change. Well, but the air temperature, you can see the air temperature is really the change we really collected with our the C4 plants. You can especially for the summer air temperature. So currently studies show that actually C4 plants abundance increase significantly when the mean summer mean annual air temperature extends to 8. So here you can see since 8 the temperature is almost more than 10. So we think that this because the warm temperature so caused the C4 plant extension. And also we calculate the parallel elevation. We find that it's a little bit low elevation. So here conclusion. So we provide direct evidence about the C4 extension in the Himalaya hinterland and show it occurred earlier. And the regional factors, especially the elevation and the temperature, are more than the monsoon. So we think that the modular elevation in landshot settings have reached the climate tipping points for C4 dominance before the subcontinental extension. That's all. Thank you.
Thank you, Chinken. So we reached the point for a discussion on all the previous 4 talks, and we have some time for this. So please raise your hand if you have a question to one of the speakers. Otherwise, I start with a question to Alex. Of course, when you go back in time to about the India-Asia collision, then you have many uncertainties. And you also raised these comments to Booth in Kwangsberg. What about the effect of the Indian subcontinent? Because there's a discussion of a much greater Indian plate during the collision, and this will, if it was so large, also hold on for tens of millions of years. So which effect you would expect?
Yeah, that's a really good question. And, you know, we do model that as well, so I can look exactly at what that effect can be, because we do have a greater India, quite a large one, especially reaching the beginning of the beginning of the Cenozoic onwards. And again, you do see some local heating, but it's not strong enough local heating to dominate what's going on atmospherically then and there in Greater India and south of the Gangeji compared to other factors that are having it. What you really see is a sort of mid-tropospheric airflow coming from the north and skirting around the Ganges, and then it's interfering with all that deep convection, capping it in mid-atmosphere, so it can't get high in the atmosphere and develop all this strong rainfall shadow into it. So we do have that, you do have an effect, but other factors are, I call it that instability in the monsoon in that region.
Kasim.
I would like to ask a general question, since there are several people, experts on rainfall climate. The global warming is going to increase the area of the oceans, and with that there will be more humidity in the atmosphere. Is it going to remain as humid, or is it going to be more rainfall in the world?
Yeah, that's a very, very good question. And, you know, we can certainly tell from the modelling that has been done already with the IPCC what's going to happen in the future. As you warm, every 1 degree of warming of the atmosphere, you tend to increase its moisture holding capacity by about 7 or 8%. That's known as the sort of Clausian-Clapeyron relation. Now, that doesn't necessarily relate to how much wetter it will get, and that's a lot of disagreement at the moment exactly, but sort of satellite observations sort of suggest every 1 degree of warming might lead to about maybe 3% increase in precipitation. However, the problem is when you look into the future, especially at all the different IPCC CMIP6 results, they vary considerably about what they think the monsoon is going to do. And that's pretty much because all these models have different skill at representing monsoon systems. You know, we're fortunate for our model. We have a very good model which does do very good, skillful monsoon predictions. But again, it's very uncertain exactly what the world what the monsoon will look like in the future, because there are so many other factors rather than just that thermal warming on the atmosphere and extra moisture holding capacity will do in that in this setting.
Here's a question for Professor Deng Tao. My question is, where is the snow leopard original? You shown the cold mammal is go out of Tibet, but as you shown, lots of snow fossils have been found in North American and even South American. So my question, where is the snow leopard original?
Okay. We think along the upper left of the Tibetan Plateau, so the slow area in the Tibetan Plateau, at least in the Pliocene, the all area become the very cold environment. So the cold adaptive the mammals arranging in the Tibetan Plateau, maybe from at least in the west part and the north part. For example, we find evidence from the Janda Basin and the Kunlun Pass the basins. We'll find a lot of.
But you show lots of fossils discovered in North American, even South American.
For example, cover the North America. Yeah. In the beginning of the Quaternary, along the ice age.
Oh, it's much younger.
Yeah, much younger. In the about the 2.5 million years ago, is the sea level the increase. So Berlin Strait became the land bridge. So they are ranging from the Tibetan Plateau across the corridor reach North America and reach South America. Thank you.
I have a question to Junjing. How do you discriminate about the aeolian source for the Loess Plateau, that it comes from the Taklamakan and not from the Chidon Basin?
Yeah, we use that mainly using the detrital zircon geochronology data based on the different peaks. So like it's from the northern part of the Kunlun Mountain. I forgot the exact peak. It's more abundant, seems like 400, 500 linear age and more abundant. If it's from the local source, so the 200, 300 million years are very abundant. So we try and using the detrital zircon as the tool to discriminate different sources. Thanks.
Is there another question? So,
Even though I have
yes.
another question for Professor Dai. The famous work done by J. Quitt, the C4 plant is original from South Asia. But based on your work, from South Himalaya, the C4 plant is original maybe from Himalaya. It's a little bit early than South Asia.
Yeah. Thank you, Professor Dean. Yes, our study really local and really small basin. So yeah, we think compared to previous study, our finding is a little bit earlier, about half 0.5 MA, earlier than the results from the Siwalic Formland Basin. So we think that because of this is a little bit high elevation, but it's not so high. So but it's also in the land show of the crest, the Mount Everest and Xixia-Baoma. So we think that this really unique topography settings may be induced or a little bit earlier triggered, a little bit earlier C4 plan. And here we want to emphasize the temperature, local temperature maybe it's more than important than the CO2 level or some other factors. Yeah.
Okay. Thank you.
Thank you.
Okay, now we are perfectly on time. There is no break now. It continues with the session. Thanks to the speakers. Now it changes to the next group of speakers. So please, speakers of the next group, come up to the stage.
Okay, thank you. Yeah. Okay, I'm very happy to chair this second half of our session. And the first speaker from the Shanghai University, his team is, say that please. 没事。 The first the topic is the Asian summer monsoon, the evolution and the driving mechanism.
Okay. Thank you, Professor Deng. I'm Chao Fengfu, come from Taiwan University. I'm very pleased to hear take part in the second PlateauPlus International Workshop. My topic includes in 4 parts. The first introduction. We know complexity of the multi-scale Monceau dynamics from geologists' perspective. There are 3 time scales, including tectonic scale, orbital time scale, and the millennial scale. From this picture, we can see these classic curves. Climate fluctuations is at low. There are peaks, there are values to find the causes and the loss of the climate change. In the orbital scale and suborbital scale is a research direction of Earth scientists. Especially paleoclimate researchers have been working hard and looking for historic analog of climate change becomes the basis for future climate prediction. This is a good example for historic analoging of climate change. Previous study comparison of the East Asia winter monsoon and summer winter monsoon practice records in Laos. In past 90,000 years, this study predicted the next 40,000 years summer monsoon change. The premises of future climate, the prediction to find a high resolution climate carrier and accurate dating. Look for orbital time scale or millennial scale analog of climate change and understanding the driving mechanism of climate. Our work is carried along this line of thinking. This is my study area. In Jiangxia Basin is located in the northeast Tibetan Plateau and contains a sync sequence of Cenozoic sediment which can provide a record of evolution of Asian monsoon environment. A previous study caves sink at the beginning of the Eocene. The Indian monsoon has not reached the study area because of the high mountain barrier. This is a Jiarang section conditions. We can say Loess cave coupled enriched near vertical joints. This is typical aeroline characteristics. The Jiarang sections divided into the Xiadongshan formation and the Jiarang formation. The sediment faces is main aeroline dust. The secondary dating study. This is my magnetostratigraphy results. The established time scale is 1188 258 million years by spectrum analysis in depth domain, there is a stable 26 centimeter cycle represent non-eccentric period through TFD proxy. Sixth paleomagnetic age was selected. The 11.788 to 5.89 million years is established. Thirdly, Asia salmon monsoon evolution records from Jiangxia Basin and is driving mechanisms. The magnetic sequences, Robotium and strontium. Robotium to strontium ratios is East Asia salmon monsoon proxy. From this picture, we can see there is 80.5 million years and 7.2 million years is an important time dot. The correlation of TFD and TFD percent with TLF indicated that before 80.5 million years, the sediment underwent a weak chemical weathering process. After 80.5 million years, the sediment underwent a strong chemical weathering process. Raise two questions. One, why do climate parameters change significantly at about 7.2 million years and about 80.5 million years? Two, what are the characteristics of late Mersenne summer monsoon precipitation trends on orbital time scale? Has any implications for future climate change projections? Spectrum analysis, possible explanations in tectonic time scale for the growth of the northeast Tibetan plateau, and especially after about 7.2 million years, the East Asia was mainly affected global cooling and ice build-up. Possible from 11 million years to 80 million years, the summer monsoon precipitation is dominated by the weak 41 kiloyears obliquating period and strong 178 kiloyears obliquity period caused by gravitational perturbations from Jupiter and Saturn. About 173 kiloyears orbital cycle is the driver of changes in the Asia monsoon system and influence on the global carbon cycle. From 85 million years to 2 million years, the summer precipitation is dominated by the strong 41 kiloyears obliquity variation period of the Earth. Coupled with plateau uplift, the 40 kiloyears cycle-driven Antarctic ice sheet, nor albedo and warming, which strengthens the Land Sea as the more contrast and the East Asia summer monsoon. From 7.2 million years to 6.1 million years, summer monsoon precipitation is dominated by the 100 kilo short eccentricity variation period of the Earth. The combination of Antarctic ice expansion, Asian and artificial atmosphere CO2, decline, tectonic ocean current tiering, and Mosinian solid crescents, and initial Arctic ice formation. From this picture, we can see climatic parameters of the Arlene red clay, typical Loess and deep sea. In 7.2 million years, there are various period shift from 41 kilo years of liquid period transfer into 100 kilometers eccentricity period, which is similar to the climate transfer around 0.9 million years in the middle plateau typical plateau. The 10 kilo short eccentricity set comparison from the Jianzha, Baoji, Lingtai, and Chaola section. We can see there provide a new analogy for prevailing field monsoon climate changes. More research is needed. Summary. This is my thought. Thanks for attention.
Thank you for the Professor Fu. Thank you. Sit down, please. Now we move the next speaker, the Professor Feixiang Wu from the IVPP of the Chinese Academy of Science. His title is Succession of Fish Fauna in Tibetan Region since the early Mesozoic.
Thank you. Good afternoon. And it's very glad to share the discoveries of the Mesozoic marine fishes from the Himalaya. My name is Feixiang Wu from IVPP, Chinese Academy of Sciences. And what? Yes, geological data show that the basic topography of the major part of today's Tibet Plateau results from the long distance drift from the south hemisphere and closure of Texas, which should be witnessed by the past lives under the water, for example, the fishes. And indeed, the evolution of Texas changed not only the land-sea distribution along the continent, but also the routing of the life history. Numerous data suggest that the phasic volcanism and its consequence in the Texan region might be one of the major killers of end Permian mass extinction, the most severest among the big five. And this disaster reshaped the ecological structure of the system, both in the marine rim and on the land. And in the marine environment, the four-legged animals, for example, the ichthyosaurs and numerous new fish killers began to take over, and they reshaped the structure of the food web there. And fortunately, several episodes, some of these episodes were locked in the mountain, in the stones of Himalaya. And in the mountaineering scientific expedition for Zumulama Mountain about 16 years ago, a very strange fossil teeth were discovered by Chinese paleontologists, which was named by Zhang Mingman, Professor Zhang Mingman, and with the name of Cynohelicoprion. And it is really a very strange shark because it was equipped with spiral teeth, And with our revisit to the materials by using CT scanning and restoration technology, we can see that the biting behavior, the biting behavior of this shark was profiled in the combination of the sharp teeth, snout, and the snout teeth in the mouth. And with the Tibetan material included in the complicated analysis for the function, we can say that the cutting function of the teeth of this family was actually much diverse, more diverse than previously thought. And apart from the sharks, bony fishes, for example, lizard fishes also left very important footprints in the Himalaya. For example, the saurischids, the lizard fish, the kind of bony fish that looks like the ichthyosaur, but they are the close relative of the living sturgeons. And the fossil records of saurischids or lizard fishes came from the Nepal and the Kashmir from the early Triassic deposits, just before the rapid diversification in South China, namely the eastern part of Paleothesis and the western part of Paleothesis in Alpine region for this group. And these saurischids records or members from the remote South Hemisphere were also linked with the allies in fresh waters from the Lower Asia land masses, for example, from Xinjiang, the northwestern parts of China. And shadowed, based on our study and the restoration of the family tree of this group, we can say that shadowed by the freshwater environment, this group, some members of this group in the fresh waters, they held some primitive features of the ancestor lineages from the southern hemisphere and avoided smaller extinctions in the marine environment. And you know, in the Triassic marine ecosystem, ichthyosaurs were the king. But the fossil records of these marine reptiles can be only dated back by the late Triassic, but also from the localities around the Himjumolama, namely named Tulong of Nielamo County. And yeah, namely the reptile was named with Himalayasaurus. And the best preserved material for this creature was discovered by a paleontologist team led by Qiu Zhangxiang, a then young graduate from the University of Moscow. And they were really impressed by the fossils because it was a very huge ichthyosaurus. And based on the scales, whose estimated body length can exceed more than 15 meters. So it must be a very huge or very successful predator in the ocean. But what fed such a huge killer? Yes, partially the fishes. For the same locality of Himalayasaurus, paleontologists have collected numerous teeth of hypodont shark and a kind of very strange bony fish named by Bearia or saurischids or lizard fishes. And so when we include all fossil materials collected from the locality of the ichthyosaur, we can see the complicated ecological system dominated by the ichthyosaur was established already by the time in the remote areas in the southern hemisphere. So when the Lhasa block approached the docked the Chantan blog, in the age of dinosaur. The Jurassic fossil fish from the southeast Tibet show that there are many species of global distribution, and for example, the hibernal teeth. And also, the paleontologists also discovered some lineages that show some affinity to the counterparts in the remote areas, for example, Australia. For example, the lungfishes. And more importantly, that we also have noticed that some of the species are very, very important ecological role in the fossil communities. For example, the pickled fishes. The name meaning the fishes with really hard teeth. So, according to our, functional analysis for the teeth of the fish, we can say that both the morphology and the arrangement of teeth of the fish is very useful for them to crushing hard shells and make them a very important builder of the basic community in the fossil localities. And this is the big picture of the dinosaur fauna, which includes the fishes referred above. We can say that this should be very important transformer in the bottom water by consuming the hard shells. So, in the eyes of the fishes, the dinosaur, okay. So, in the eyes of the fishes, the dynasty of Tethys should be divided into two parts. In the episode of Triassic, we can see many lineages of global distribution. And more importantly, we can see through the fossils that a very complicated marine ecosystem was well established in the southern hemisphere by late Triassic. But the affinity with other fossil assemblages remains unclear because of the limited material of the fossils. As for the Jurassic episode, we can get important information about the fossil fishes. We can say that acting as the prey of the dinosaur or some other aquatic vertebrates, the fishes from the southeast Tibet should be a very important role in shaping the basic communities of their time. So that's all. Thank you so much.
And the second is for Professor Wu. Now we move to the next speaker, the Dr. Dan Hui-sun from IVPP of our Chinese Academy of Science. Her title is Evolutionary Insights and Paleoecological Reconstruction of the Miocene rhinoceros in the Ningxia area, northeast China. Please.
Okay, thank you. Good afternoon, everyone. My name is Dan Hui-sun from IVPP Chinese Academy of Science. And today I'm very glad to be here to share some research results to all of you. And my talk today is about the evolutionary of the rhinoceros in the Ningxia, in the Tongxin area. Oops, okay. So let me introduce the background of the rhinoceros. As we all know, the modern rhinos is endangered. As you can see from this picture, there are only 4 genera and 5 species living in the world. Like this is the black rhino and white rhino. They have 2 horns, which are living in the Africa. And there are also 3 species are living in the Asian. And although the living rhino is almost extinct, but in the geology time, there are so many and there are extremely abundant rhino fossils are recorded. As we can see from this distribution map of the rhinoceros, they were originate from Asia in the Eocene, and they can come across they can go to the North American through the Berlin Street, and then during the Miocene, there are many diversity and extremely abundant rhino fossils we can see during the Miocene period. And the last, the rhinoceros become less and less, and now the living rhinos only 4-5 species. So we have summary about the Miocene rhinos in China. As you can see from this chart, this is the number of the general of the rhinoceros. And we also list about the evolution about different rhinos in the Miocene. Okay, help me. Oh, yeah, there are 4 stages. 4 stages. This is 1 stage, 2nd stage, 3rd, and the 4th. They are different character and different numbers of the rhinoceros. As you can see, in the early Miocene, they are similar with the Oligocene rhino fossils, but in the end of the Miocene, they are different species with the early time. And luckily, we can find a lot of fossil materials in the Tongxin area. And Tongxin area is just located at the northeast part of the Tibetan Plateau, and it was influenced by a lot of tectonic movement. So there are so many sedimentaries of the stratus deposit in the Tongxin area. As we can see, it's a very thick sedimentary here, and they have yards, so many beautiful and very complex large mammals. And the rhino fossils is just one of the representative. So, go ahead. No, yeah. So according to the characters of the different fossil rhinos, we have summarized the materials belong to 4 genera of the rhinoceros. Okay, let me introduce it in details. So this one is the first materials of the rhinoceros. This one is very special because, as you can see, this is a nasal bone. This nasal bone is very wide and very thick, and there are some raw surface here. So it was indicated there is a small nasal horn in this rhino. And we can see from the cheek teeth, this is a premolar 1, 2, 3, 4, and this is a molar. This white part is a cement. It's a very special part of the cheek teeth, and this cheek teeth was covered by plenty of the cement. And so we compare with other species. This is a new species, Tongxin therium. And let me introduce another materials. Yeah, this is another one. This one is was special because the nasal bone is uplift, and it's also a very rough surface here. So they also have we make a construction about these materials. They have a small nasal horn on the end of the nasal bone, and the cheek teeth. Look at the cheek teeth. There are very complex structures on the cheek teeth. This is a special structure. It's a protocol, and this is a hypercone. They were connected with each other by the lingual bridge. So there are some special characters of these rhino fossils. And let me introduce the third one. No, go ahead. Oh, okay. Oh, this one. This one is different from the mentioned just now. Look at the nasal bone is very flat and very long. And so this is a hornless rhinos. It's different with the modern ones. And let's look at the occipital side. It was inclined forward. It's also different with the white rhinos which are living in the African island. And this one is the last one materials from the Tongxin air. And this one has a very, very special part. The premaxilla part, they have the incisors. These are very special characters of this general. So according to the paleontologists, I just mentioned now, we summarize all the characters of the rhino fossils, and including the skull characters, mandible characters, and teeth characters, and also the postcranium characters. And we make this matrix, and we can have a phylogeny trees here, and we can see this is a result of the phylogeny before. And later we have more materials, and including the Tongxin materials and other materials from Africa and Asia. So we make this phylogeny tree here. So according to the phylogeny, the relationship between the modern rhinos with the Elasmosaurus, and we have summarized the evolutionary trait of the rhinos. As you can see, obviously here, the body become very large, and also there are some characters between the teeth. This is the former one, this is the latest one. They become more complexable on the cheek teeth. Okay, besides, we also have reconstruction about the paleoecology of the air. And you can see this is a logical character and also the pollen analyzed here. And I can see from here, this is the black, this is a white rhino. This was a totally grazer. And this is a Java rhino, which are living in Indonesia. And this one, this is the occipital side. Like the black rhino, this is a white rhino. White rhino is totally grazer. They have the back, it have the back forward, the occipital. But this one was inclined forward. So according to the modern ones, we indicate that the fossils maybe have the humid environment. And also, like this is the Elasmosaurus, like the teeth, I just mentioned that there are so many, the sediments covered on the cheek teeth, so maybe it was living in the grassland. It's very open grassland, so we make this reconstruction about the Tongxin cerium and the placenta rhinos. So according to the modern ones, like the white rhino and the Java rhinos, occipital side, we make the environment reconstruction. And I mentioned, we make a summary about the paleoecology of the Tongxin air. And in the this is the late early Miocene, this is the middle Miocene, and this is a paleoecology reconstruction, and we just make about this result. And that's all I want to share with you today, and thank you so much.
Oh, thanks for Dr. Sun. Now we move to the last speaker of our session, and Dr. and her is the communicating the multi-hierarchy risk and information in dying plateau for sustainable the regional. Please.
Thank you. Good afternoon. Okay, my name is Asteria. I'm from BMKG Indonesia. I would like to share with you our preliminary study in Dieng Plateau, Indonesia, in Central Java. entitled Communicating Multi-Hazard Risk and Information for Sustainable Regional Planning. So before I start my presentation, may I ask if, for you to raise your hands if you ever been involved in science outreach or community outreach before? Oh, wow, thank you so much. So I think you can imagine the complexity in dealing with the local community in sharing your scientific information. So that is what I would like to share today. Okay, the outline of my presentation is like this. And the first one will be the background. So from my literature study, I concluded that plateau regions globally are facing intensification of multiple hazard risks, either from the geomorphological, from the geological, or also from the atmospheric dynamics. Everything is so complex in the plateau because of their morphology. And also we have the climate change to add to the complexity. And from one of the literature that I found, by Meredith et al., 2025, she mentioned that Southeast Asia has the highest number of exposed city population to volcanic hazard. So I think this study is pretty significant for our region here in Southeast Asia. And so the objectives of our study is first to gain a comprehensive understanding of the multi-hazard risk in the plateau, to be specific, and then to examine a better science communication approach for sustainable regional planning. The significance will be that the effective and inclusive science communication approach will help in the building or developing community resilience, and also will be helping in the co-creation of sustainable regional planning. Okay, I would like to share this one, a particular approach in the plannings. This is from Einstein, 1969, but still relatable until now. So, commonly, planning from top to bottom. Only the planner, only the decision making who will make the planning. But how about the voices of the local community? So usually it will be like this, only informing like the researcher, the scientists, the government inform their scientific evidence, information to the community, or maybe consultation. But what we aim here is partnership and also delegated power, because we, from the science side and also from the government side, we cannot just assume that we know everything, that we can solve everything, especially in the face of multi-hazard risk. We need the local community to work together with us and plan what next, what is better for the future. And so that is how I come to this study. This is Dieng Plateau in Central Java, Indonesia, located in the Wonosobo Regency. And Dieng Plateau itself covers 1/5 of the whole area. The demographic, around 728 people per kilometer square. And mostly they are farmers, like potato and also vegetable. And also because this is like highlands and also volcanic complex. So many, like geothermal and also tourist site. And the morphology, from what I discovered, that mostly more than 2,000 meters above sea level. So the temperature itself usually around 20 degrees Celsius in the afternoon and maybe around 10 at night in the evening. And the land use cover mostly like rice field, tea plantation, tobacco plantation, farm fields. But because we have this like sudden drop of temperature in the dry season, we have this environmental issue. It is the frost event. You can see here the cabbage here. The frost event, it similar to like having snow in Indonesia. Every dry season we have this, and many people, like domestic in particular, they want to experience like snow. Usually they come to Dieng Plateau and they experience this. This become a very popular tourist destination. But because of the morphology, the region is susceptible to multiple types of hazard. Earthquakes, phreatic eruption. For instance, in 1979, 142 lives were lost. We also have like landslide. Every heavy rainfall, it is very risky to have landslide there, and also the frost event. And according to Jenkins' study in 2022, the population exposure index is quite high. It is 7. So I think it's we need to take this into consideration. And the hazard risk agents, if I may say, we have the monitoring institution that day-to-day basis monitor the site. From the Ministry of Energy, we have the Center for Volcanology and Geological Hazard Mitigation. They monitor earthquake signals and eruption events. We also have our institution, BMKG. We monitor not only the earthquake signals, but also the weather and climate parameters there. And we also provide the multi-hazard early warning and information. We also have, for the disaster management, we have the Disaster Management Agency. But because of the livelihood there, we need also Bapeda, or the Regional Planning Agency, the private sector, and NGOs to be involved. So usually, the community approach can be shown like this, only like informing, only like a lecture, but it's not really enough to ensure the sustainability of the awareness and also on the planning side. So we would really like to ensure that we involve all the local community in having like a dialogue, because we would like to hear their voices, their concern, their risk perception, cultural beliefs that may be like stand in the way of how they will be able to collaborate with us in the reducing the hazard risk. We would like to ensure that no one is left behind, no voice is left unheard, and no perspective is unacknowledged. Because that is what the sustainability in the community resilience is. So we would like to propose this geodesign framework. It's a kind of like a workshop with involving the geographer, the design profession, information technologies using GIS, the map, and the people of the place or the local community and the stakeholders. And with these iterative models, we would like to see like a dialogue to improve the awareness and the understanding of the local people on the hazard risk that they have in their region. And so the summary is that the population and environment in the Plateau region is highly susceptible to multiple hazard risks. And there is a gap in the risk and information communication approach, because the level of risk awareness and understanding, especially from the local people, is still like sectoral basis, like tourism basis, like farm basis. So it's not really like interdisciplinary. So to ensure the regional planning in the future, we need a more effective and inclusive multi-hazard communication approach. So that is all from me. Thank you for your attention.
Okay. Thanks for Dr. Astera. We just finished the 4 presentations of our section about the monsoon, about the fish, about the rhinoceros, and about the herald. What's some question for them? Any question? I have a question for Professor Fu. Just you mentioned the northeast part of Tibetan Plateau about the monsoon, depending on the ionic dust. We know, for example, in Nanzhou Basin, the ceroloic the deposit from the Paleogene to the Neogene to the Quaternary, for me, it's very similar in kind is red deposits. How to distinguish, for example, lacustrine, fluor, and the ionic, the dust?
Thank you. Jianzhou Basin is located in the northeast plateau. The Nanzhou Basin have some lacustrine sediment and adjacent Jianzhou is to west is the Xunhua Basin. Is some in Xigou section is a lacustrine sediment, but to the west is Eolin dust sediment, because we do some experiment. Example for Loxnesis, the grass size experiment, it look like Chinese plateau, Chinese Loess plateau. Example for Zhuangnang section and the Qin'an section. So it is early dust, so can throw it, can study the at more recent current winter Asia winter monsoon and Asia summer monsoon. Yeah.
Any question? Dean?
I have a question for Sun Danhui. There are lots of huge animals in North Tibetan during Miocene or late Miocene time. I just want, what's the flora in the same time? What's the animal eat?
You mean the large animal?
No, I mean the flora, the plant. What's the environment during that time? What's the kind of plant, flora, 植物?
I know that. I mean, we just, according to the structure on the checklist, we just know it's a grass or plant or it's a leaf. We don't know exactly which species or which kind of.
That means you have found leaf fossils in the same layers of the animal fossils.
Is after the coffee break?
Yeah, maybe, but we don't research about the leaf fossils. So yeah, maybe it's a very good suggestion. Later we will combine the leaf fossils.
Yeah. You have found many leaf fossils there, huh?
What?
The leaf fossil.
I know that.
What kind of fossils? The plant.
Just the large mammal fossils.
No plant fossil.
No. But we don't study the plant fossil.
Okay.
Sorry.
Okay, thank you.
Thank you.
And any question?
Me?
For
From
other
this
speakers?
side. Excuse me.
Well,
Thank you very much. My question for Dr. Asteria. Yeah, maybe a bit comment from your presentation. Thank you very much. So, do you agree, I mean, do you think it is good for serving the multi-hazard approach to the community? Because I think one single hazard, it is also difficult to communicate to the community. So having many hazards, then we have to communicate the level of hazard, the meaning of the level hazard, and so on. So, yeah, maybe how do you see this problem? Thank you very much.
Thank you for your questions. Hazard or natural hazard in particular, actually, in my opinion, we cannot box it into only one study field or the other, because what happened in the nature is all interconnected. So that is why we need this multi-hazard science communication approach, because what happened, usually it is interconnected. For instance, for the frost event, maybe frost event can be explained by the atmospheric dynamics, what happened in the atmospheric dynamic. But actually, frost event will not occur if it is in the lowland. So at the same time, we also should explain to the local community about this morphological and geological. So actually, it's multiple. It is interdisciplinary study. So I understand that maybe it will be a little bit complex to explain that, especially to the marginalized community that maybe they don't really educated, their education level is not, but actually by having to explain that to them, making them understand, and also we learn from them how actually they see what happened in their area according to their perspective, maybe we can learn also from them. So in that communication, in that dialogue, we can achieve together a new understanding. So, well, for me, whatever it is complex and challenging, if we can accomplish that, we will be able to achieve greater understanding and together. Hope it helps. Thank you.
Thank you.
I have a question for Professor Feixiang Wu, and I'm quite interested. What causes the extinction of the top predator in the Himalaya? The extinction of the shark.
How many species?
The reasons that cause the extinction of the Himalaya, the shark.
Extinction.
Shark
mean
fossils.
early Triassic or late Triassic?
Yes.
As for the early Triassic locality from, namely the Halties, there's only one record of this fossil. But for late Triassic locality, namely from the locality of Himalayasaurus, there are at least 3 lineages from the fossil records, namely Bearia, Hypodont, and or even the lizard fish, based on the teeth. Okay.
And why it disappeared?
Why disappeared?
Yes.
Yes. You see, all of these species are of global distribution during the Triassic period. If we, for example, but for extinction for each of this group, it really depends. For example, the Saurischies, you see, this lineage has a very long span from the end Permian to mid-Jurassic. For the extinction of this group, it is a Jurassic story, nothing with the Tibetan Plateau. But for other lineages, you see, it just appeared in Triassic in the Tibetan region, but there's nothing with the extinction. It's just a small time span for these groups. So, I think if we find, if some lineages we have some fossil records in the ending of the history of this group, we can say that there's something with the extinction with the Tibetan Plateau. But for the no species, I think nothing with the Tibetan or rising or Tibetan Plateau. Yes, thank you.
Okay, thank you. All the speakers are our session. Now we have 15 minutes for coffee break. After the break, we continue to keynote presentations and another session. Okay.
Sesinya ini langsung kayak yang pertama tadi. Sini. Oke. Tidak ada. Balik dia. Anjay. 15 menit nih. 5 menit nih juga sebelum mereka kesini lagi.
Oke, oke. Oke. Apa? Kopi. Oh, udah jadi.
Ladies and gentlemen, all participants, while you're having your coffee break, I would like to announce something about the field trip that will happen on tomorrow, 27th of November 2025. So for all foreign and also invited participants for this field trip, you must know anything or details about our field trip, because we would like to make sure that the field trip runs smoothly. Can you go next? So, previous slide, please. So we are going to Tangkuban Perahu volcano. It is a volcano near Bandung City. It has pretty big crater, and we are going to learn something about this volcano tomorrow with someone from University of Pajajaran Bandung. And next, as per our data today, here are the list of registered participants. So if you would like to, if you don't find your name in this list and you would like to join the field trip, you can come to this desk and see my friend Firzi with the vest over there, and just say your name, and then we're going to put your name on the registered participants list. We're going to display this again after this, so don't worry. Next. And this is the details for participants who are staying in Grand Orchards Hotel. Please gather in the ground floor at 7:15 a.m. local time, Western Indonesian time. And please already eat your breakfast before that. The breakfast will be served start from 6 a.m. So you still have 1 hour to have your breakfast. And there will be 3 cars waiting for you at the ground floor. And for participants who are staying in Orchards Industry Hotel, the assembly point is the same in the ground floor, and you have to be there at 7 a.m. So it is earlier, a bit earlier, and there will be only 1 car waiting for you at the ground floor. And please do the same as people in Grand Orchards. Have your breakfast first before this time. The breakfast time start at the same time, which is 6 a.m. And we would also like to suggest you to wear comfortable clothes for outside or outdoor activities, because we're going to, outside basically. And it is best also for you to wear sunscreen just to protect your skin against the heat and also the sunlight. So, Mas Harfan, please go back to the previous slide. Yeah, okay, so again, please, if you don't find your name here and you would like to participate in the field trip, just come forward to this desk. Thank you. And if you have anything to ask, just, yeah. Cek. Yang nama tadi aja, Mas. Nah, ini aja udah. Check. We will start the next session in 4 minutes. Ladies and gentlemen, we are about to start the next session immediately, so please have a seat. And we're going to see more interesting talks in the last session, which is the 5th session, Modern Climate Surface Processes and Disaster Risk Reduction, which is going to be chaired by Professor Min Feng and also Professor Morteza Talebian. And it also includes one keynote session from Professor Irwan Meilano. Yes. For all speakers and also the chair, I would like to invite you to come forward to the stage. Ladies and gentlemen, please have a seat as we are about to start the next session immediately. And for the session chair for this session will be Professor Min Feng and also Professor Morteza Talebian. And there will be 7 talks and 1 keynote speaker for this session, which is from Professor Irwan Meilano. So please have a seat and we will start the session immediately. And I would like to invite all of the speakers, Professor Min Feng, Dr. Weniza, Dr. Yong Ni, Dr. Shinshu, Dr. Yong Sun, Dr. Ida Pramuwardani to come forward to the stage. Okay, so because all of the speakers are in the stage already, I would like to give the opportunity to lead the session to either Professor Morteza Talebian or Professor Min Feng. Please, time and place is yours.
Good afternoon, everybody. So, please come and sit. We are going to start the last session of this conference. So there's a small change in the program. So we'll have Professor Irwan Meilano as a keynote speaker for this session. And he will be presenting Unlocking Earthquake Potential Through Geodetic Science. So, Professor, are you ready for presentation? Yes, okay. So please.
Thank you for the introduction. Good afternoon, everyone. I'm very delighted to meet all of you today. Could you please someone help me with the slides? I hope. Okay. Well, as already explained by the moderators, I'm Irwan Meilano. I'm from ITB, Institut Teknologi Bandung. And today, probably slightly different with already been discussed for the last few minutes, I'm going to share with you what we have done in understanding tectonics of Indonesia by using geodetic data, by observing the crustal deformations in Indonesia. And please continue to the next slide. Well, there are 4 different topics that I would like to discuss with you today. The first one is the tectonics of Indonesia, and the second one, the earthquakes potential. The third one is how we use our approach to observe the dynamics of tectonics in Indonesia, and then the result, and finally what lesson that we can learn from our research. Please continue. We have done this research for the last 25 years. We've been observed the genetic motions, deformations model in Indonesia since 1998 or 1997. So we can say quite complete models of the deformations in Indonesia. As you might aware that Indonesia is a very good research, as a good place to do a research in terms of the tectonics. We are a place that at the same time we can study the subductions, the collusion, and also the transform. We have the subduction in the west part of the Sumatra, southern part of Java, and we go more to the east, we have a transition zone from the subduction into collusions. And in between, in the middle, we have a transform area. So it is a very good place to test many methods, to apply many approach. Please continue. Well, this is the earthquake data that we have plotted. I think the data is probably the data since 1960s. So we try to plot the earthquakes data in the regions. The message that I'd like to share with you that you can clearly see the good associations between the tectonic process with the earthquakes, but you might also see from these figures that I'm not sure if it is working, that showing by the red ellipse, you can see some areas that we don't have a big earthquakes in the last 30 or 40 years. This area is very interesting to be studied, and currently we are doing some research on this area. And I'd like to share some our published papers related to the area showing by this red ellipse. I hope it won't take a long time. Please go to the next slide. As you might be aware that our approach is very simple, and by assuming that we have a kind of stages of the earthquakes, the strain accumulation and release. So an accumulated strain as a function of time will release suddenly as an earthquake. But it is not as simple as that. I'm going to show you the time series data in some area of Indonesia. That sometimes we need also to study the post-seismic deformation associated with the earthquake, which is very complicated. Or maybe we found an evidence that not clearly related with the earthquakes, but another, for example, slow slip events. So this kind of model is very simple, but to be honest, it's very hard to be applied in real data. Please go to the next slide. Well, it's very old papers. It's a very good one, but the reason why I show you this slide is just to give you an overview why understanding the earthquake potential is very important. In terms of, there are two issues. The first one is by understanding the seismic potential, then we can produce the good seismic hazard maps. That's the first one. But the second one, which is also very important, by having a good understanding of the seismic potential, to some extent, we can do what we call as a medium-term earthquake predictions. Not a short-term, but a medium-term. There are three kinds of approaches: the short-term, the medium, and the long-term predictions. So, by having a good understanding of the earthquake potential, at least to some extent, we can produce a good seismic hazard map. And the second one, giving an overview about the medium-term activity of the earthquakes, or what we call as a predictions. Well, what we have done for the last 20 years, we tried to compare two different data sets. The first one, showing by the red lines, is we calculate the earthquake moments. We calculate the moment for every earthquake in the region, Indonesia. And the second one, we calculate the moment accumulations that we obtain from the strain accumulation from the geodetic data. So we have two different sense of the moments. The first one, the release moment, and the second one is the accumulation moment. So the message is very simple, that the accumulations of the moment will be released someday as an earthquake. So by having a very good data set of the accumulated or the release moment and compare with the accumulations, then we have a very good sense of the earthquake potential. Please continue. And how we do that? How we calculate the accumulate of the moments? It's very easy to calculate the release of the moment. So if we already have the earthquakes, then we can simply do the, for example, inversions to calculate the slip distribution of the earthquakes. We can do the inversion by using teleseismic data or combining the high-grade GPS with the teleseismic data to calculate the moment rate functions. And having this information, then we can calculate the moment of the earthquakes. But the question is, how to estimate the moment of the accumulations? Then what we have done, we use a geodetic data, we estimate from the transient deformations, meaning the deformation without the earthquakes. As you may see that this is the data somewhere in Sumatra, showing the data in the lower right. So you can see the transitions. I think the blue line, the blue dot showing the vertical, the horizontal components, the EW, north-south components, and the north-south component and EW, east-west component, and the x-axis at the time in years, then you can see that it is for the last, I think for the last 20 years, we can clearly see the time series of the GPS. And we convert this information into the strain. But you can see also there is a jump in the data, meaning there is an earthquake, and there is a kind of exponential decay. It is what we call as a post-seismic deformations. So by using this data, come from hundreds of GPS stations in Indonesia, then we can estimate the earthquakes accumulations, the accumulated moments of the tectonic process. Please, next slide. And then the idea is very simple. So you may understand that it may take 1,000 years, 2 years for the tectonics process to accumulate the strain. But of course, our data set is very short. We just only have data, as I mentioned, for the last 20 years. But assuming that the process is kind of linear, then of course it is not purely linear. But assuming that the process is kind of linear process, then we may calculate the strain accumulations, then it will be released as an earthquake in the matter of seconds or minutes. Please continue. And then having this kind of informations of the strains together with the informations of the fault geometry, we estimate the deformations model, then we calculate the earthquake rate models. And this earthquake rate model become an input for the probability models. And finally, we use this kind of information to estimate the probabilistic hazard analysis. Please, to the next slide. And this is the data that we use. We use hundreds of GPS data in Indonesia. It is the best data set that we have. It is not the best in the world, but it is at least the best data that we have now. We are progressing. We will improve our model, but at least we have an early models of tectonic motions, strain accumulations in Indonesia. Please continue. And this is a strain map. So we translate the deformations that we obtain from the time series and become a factors, and from the factors we calculate the strains. We calculate the principal component, we calculate the shear strain, we also calculate the dilatations, and we also estimate the second invariance of the strain. It is the magnitude of the strain. It's very simple calculations. Please continue. And of course, we have published several papers. Please continue. Well, please allow me to discuss from west to the east. This one is a paper that we published last year. We use the strain data. We use the GPS data in the west coast of Java. The west coast of Sumatra. The idea is to calculate the strain accumulations, and not only strain accumulation, but also we calculate the slip deficits. So you may clearly see that showing by the one on the right side. So you can see that showing by the white color is the area with the high slip deficits, and the red one is the area with small strain accumulations but faster slip deficits. And it is very interesting to see that the area outside the slip deficits, we found the area of the earthquakes. So to some extent, we found an area with the area where the strain is accumulated. Okay, please continue. And we also did the calculations for the Kalimantan. This is a paper just appeared last year. What we do is we compare the seismic data with the GPS data. As you might understand that Kalimantan is area supposed to be the most stable region in Indonesia, but from our GPS model, we still found quite significant strain accumulations in some regions larger than 40 nanostrain, and it has very strong correlations with the earthquakes. Please continue. And this is the one in the area between Kalimantan and Sulawesi. In this area, we estimate two different products. The one is strain accumulation before the earthquakes, and also we estimate the slips after the earthquake. So it's very good correlations between the accumulated strain and the release after the earthquakes. And please continue. And this is for the Java area. So we have done the inversions to calculate the coupling on the subduction interface in Java Islands. The message that we would like to share with you that showing by the red colors is the area of the very high coupling ratio. As you can see in the south coast of West Java Islands, and another area in the south coast of Central Java and the Eastern Java. We also calculate the strain accumulations on the active fault, inland active fault in Java Islands. Based on the information from previous published paper about the Baribis fault, then we calculate also the slip rates of some segment in the Baribis fault. So now we have a very good sense of the strain accumulations. As you may see that from my previous slide, you can see some area from the earthquakes data, we can see some area that has low numbers of the earthquake, and it has very strong correlation with the area that has a very high coupling ratio. So no earthquakes, but very high coupling ratio. So it is an area that possible to produce a big earthquake in the futures. And let's move to the eastern part of Indonesia. It is a Banda area. We have analyzed the GPS data in the eastern of Indonesia. We have a shorter period of GPS data compared to the western part of Indonesia. We have the data about 10 years or less. And by using this data set, we can estimate, we calculate the strain accumulations, principal component, shear strains, and also second invariant of strain. And it is give a very good sense if you take a look the figures on the right left, I mean the lower right, you can see a very high strain accumulations in the area in Ambon. We use the data before 2020, and we have an evidence an earthquakes years after we analyze our data. There's an Ambon earthquakes, and 2 years after there is an earthquakes in the northern part of Nusa Tenggara Timur. So we have a very strong correlations between our strain accumulation models with the release of the earthquakes, the release of the moments due to the earthquakes. Please continue to the next slide. And to be precise, this is our models, the one in the right, and on the left is the data of the earthquakes from Pak Pepen and his team. So you can see that the area of the strain accumulations is the area of the future earthquakes. And in this case, the future is not very long, only within 2 years after we publish our strain models. Please continue. So now we understand that for the eastern part of Indonesia, based on the earthquake release models and we compare it with the GPS data moment accumulation model, so we find out that in some region of Indonesia, there is a very huge significance moment of the earthquakes that not has been released yet. So it is what I mentioned earlier as earthquake potential of the future events. Please continue. And then I'd like to share with you again another kind of research. This is using the same data set, still GPS, but we try to estimate in a very short period of time the moment magnitude of the earthquakes. So we compare our calculations, the GPS data showing by blue dots with the error bar with the red star. It is from the seismic data. Just to give you an idea that we can estimate also not only strain accumulations, moment magnitudes before the events, but also we can estimate the moment of the earthquakes as a part of earthquake early warning system. This is what we have done when we compare it with the GPS data, and we really hope that this approach become a standard in BMKG. So our researchers, Pak Thomas and Pak Ajat, is working very hard for BMKG to try to implement our approach to estimate the moment magnitude by using a GPS data. Please continue. And also, still using a GPS data, so together with the calculations of the moment magnitude, so we try to use GPS data to contribute to the calculations of the P wave detections by using GPS data. And we, together with the seismic observation, of course, then now we try to apply this approach to BMKG. I think this is my last slide. Please continue. Okay, and so we use this kind of formations, the seismic hazard, the strain accumulations, the earthquake potential as an input for the seismic hazard analysis in Indonesia. So I've been part of the team since 2006, so now it has been almost 20 years. So I've been working with engineers and other scientists in Indonesia to update the seismic hazard map of Indonesia. This is the seismic hazard map of Indonesia, 1966, 1970, 1930, and 2002. This is before we joined into the team, and please go to the next slide. And this is our new seismic hazard maps. So now we have published 3 times. The first one is 2010, 2009, 2019, and the last one is 2024, last year, but become official since this year. So we use this kind of informations together, geodetic data informations, together with geological informations, and also with the seismological data to update the seismic hazard map of Indonesia. And this seismic hazard map Indonesia become an important input for the infrastructures, for disaster risk reductions in Indonesia, and also become an input for specific analysis in specific area, for example, for nuclear power plant and so on. Please continue. I think this is the last one. So there are 3 key points that I would like to discuss more with all the participants. The first one is very important to quantify the potential and long-term expected rate of the earthquakes by combining the seismic data with the deformation data. And the second one, by using the GPS data, GNS data, we can also contribute to the earthquakes early warning system, including estimating the earthquake magnitude. And the last point is having good collaborations among scientists, engineers, and social scientists. We would like to contribute to better earthquakes risk reductions in Indonesia. Thank you for your kind attention.
Thank you very much, Professor, and thanks for being on time. So we'll continue for the next speaker, and we'll have questions and discussion time. Thank you very much. So the next speaker is Professor Ming Fan from Institute of Tibetan Plateau. Please, this stage is yours. Thank you.
All right, thanks, the chair. I'm so glad to have this opportunity to talk about this topic. So this is teamwork, and the main topic is about advancing remote sensing of periglacier landforms in the Tibetan Plateau. So as you may know that about 1/5 of the global land surface is actually lying under this periglacier conditions, which is characterized by intense freeze-thaw cycles and are often underlaid by permafrost. From this map, you can see that Tibetan Plateau being one of the key distribution region of periglacier environments, and it's also the lowest latitude of the periglacier environments globally. So one of the critical threats is that periglacier environment is actually very sensitive to climate change. As we can see that rapid change in global permafrost has already responded to climate change. So the temperature change extent is actually larger than other environments in permafrost regions. Because those threats are gonna cause lots of changes in the periglacier environment, and how to detect those changes is very critical, very difficult. So one of the main things is periglacier landforms. Those landforms, such as rock glacier and talus, are the key elements in understanding periglacier environments and its changes. Also, those landforms hold significant implications for climate indication and disaster initiation, and also water resources. Okay, here. To monitoring or to detect those periglacial landforms are quite difficult because traditionally those were mainly surveyed by people in field work. We can use remote sensing, but remote sensing is especially the traditional remote sensing is not very useful here. One thing is that in those periglacial environments, the spectral characteristics are very weak. That's a very important disadvantage for you applying this kind of technology. And another thing is those complex periglacial process and periglacial landscapes, because it's a 3D process. It involves not only process on the ground but also underground. The third thing is those periglacial landscapes are usually very small. As you can see the far right picture, you can see those landscapes can be as small as like a human. So in that kind of small scale, our mid and cross resolution satellite data is very difficult to show anything. So in the past, periglacial landforms have been studied and compiled in those kind of inventory, but very limited. Like for example, rock glacier inventory has been built since the beginning of last century, but they only scattered in a small area of the globe. So one of the key advantages now we have is AI, because now the new AI methods, such as transformer, can integrate images and local features to facilitate the capture of this kind of complex and subtle morphological characteristics of periglacial landforms. So this is the opportunity for us to kind of leap forward in terms of how to study periglacial landforms. So this is the method that we developed. So we kind of combine of two things. One is a deep learning method, which utilizes high resolution, very high resolution, meter resolution satellite data to capture the unique features of those landforms. The second thing is, as those landforms usually in this freeze-thaw condition, so they kind of like show a movement, and we can use multi-time INSAR to detect this kind of movement to identify if they are moving and how much they are moving and what caused that moving. So those are the two dimensions that we try to engage in detecting periglacial landforms. So here are some examples. So you can see this is periglacial landforms, rock glaciers we detected in eastern Himalaya. This is in western Himalaya. So you can see those are rock glaciers, and the red polygons are the glaciers, rock glaciers that we identified. Not only the location, but also their extent. Okay, here are the movements that we identified in those rock glaciers. So you can see higher movements in the landforms compared to the outside. So those are the very important features that we can utilize in identify them. Okay, here is the example in eastern Himalaya that all those red dots, those are the rock glaciers that we identified. If we zoom into those two regions, you can see those small polygons. Those are the rock glaciers. And then we finished the first completed inventory of rock glacier in Tibetan Plateau, and we identified more than 130,000 rock glaciers. This number is more than all the rock glaciers in combined worldwide that we know of. So that means that we underestimate the global rock glacier distribution. and their significance. Oops, I think I just skipped one. Okay, go next. Okay, here. So now we are trying to move forward to finish the global mapping of rock glacier inventory. Okay, go next. So in addition to rock glaciers, we are also working on other landforms, including talus. So this is the first, we kind of like utilizing the similar method. So this is the first talus map for Tibetan Plateau that we recently finished. Go next. And the other landforms, especially those small water bodies like Summercast lakes on the left and glacier lakes on the right. Go next. So this is one of the water body data set we recently compiled and published in Scientific Data just a couple months ago. So this is a much higher resolution, more detailed water inventory in high mountain area, and we identified over 460,000 water bodies, and this is a much higher than what we already the water bodies that we already know. Once we have all those landform knowledge, and we can apply them to to understand our large area like permafrost. Next. So here example. So like permafrost mapping has many using in situ data, but those give us a knowledge gap in mountain area where we don't have in situ data. Next. So here we can use like rock glacier as an indicator where permafrost can exist in mountain area. The next. So here we compile in situ data and also the rock glacier records to build a model for permafrost mapping. Next. This is what we have done in Chilean mountain area. Next. And this is what we have built for the entire Tibetan Plateau, the permafrost map. And the last slide I just want to mention, all those data are shared on the National Tibetan Plateau Data Center, as Dr. Xinli has introduced in the morning. All right, thank you.
Thank you very much, Professor Ming Feng. And we'll continue with the next speaker, which is Dr. Wenizzi, and she's going to present the integrated model of tsunami hazard and human interaction. Thank you very much. Please.
Bismillahirrahmanirrahim. Good afternoon, everyone. Thank you for the opportunity. Today I would like to present about this. Okay, today I would like to present about the agent-based modeling for Pelabuhan Ratu and Jayanti village in response to the Southwest Java megatrust earthquake tsunami with magnitude 9.1, an integrated model of the tsunami hazard and human response. Before I'm going to talk about our new research, I would like to start with the challenge for the tsunami evacuation. In order to have the community in safe, not only for tsunami warning system, but also the evacuations compliance. And the second MAS 2014 also mentioned that when the community going to the safe area, the only thing about how far and how high should I evacuate. And next is about the shelter planning, location, allocation, capacity, and safety. And also about the upgraded information from the National Tsunami Warning Center, how the community react with from the upgrade information from the NTWC. Here is the seismotectonic of Southwest of Java. As we already know that Indonesia very active for the earthquake and tsunami. is located on the border for tectonic plate, Indo-Australian plate, Eurasian plate, Pacific plate, and Philippine. The consequence of this location, there are 13 megatrusts and 295 active fault. And also Indonesia have 46% of Indonesia coastline are prone to tsunami. And our new research is focused for the west part of Java, and many tsunami occurred. And one of the deaths of the tsunami is July 17, 2006. This is the objective of this study. First is to know the impact of the tsunami with the magnitude 9.1 from the southwest of Java segment on the village of the Pelabuhan Ratu and Jayanti. And the second objective is to identify the community behavior in the event of the surge of the tsunami. Why do we choose this area? This is the reason, because this area as one of the prevalent segment of the certain West Java seismic gap, and also this is the very densely populated area and among the famously recognized tourist destination, particularly for the Pelabuhan Ratu, and for the Jayanti is the very massive steam power plant. And also there is limited evacuation site that are proximate from the coastline. As we can see from this figure, there are 4 tsunami evacuation sites, and then with the sign with the red rectangular, and the yellow one is the exit as the far from the shoreline or the high hill. This is the flow chart that we have done during our new research. The first is we need to identify the bathymetry and topography data from the partners and FPI, and then we'll use the land cover from Kotani et al., and then we use the source tsunami parameter from the Babaikot 2010. From all of this, we will conduct the tsunami simulation using the COMCOT, and then we will have the tsunami inundation arrival time, and then using the spatial data and population preparation, as the parameter for the agent-based model using tsunami effect from NAS 2012, we will have the result for the casualties and the evacuation site demand. First, for the tsunami simulation setting, here we can see with the magnitude 9.1, we have several publications from the Supendi and from the Widiantoro, but on this study, we use the parameter from the Babaiko 2010, and then using the scaling law Blaster at all 2010, and we will have more than 200-fold, 252-fold. And then using the nesting grid with the 5-layer, and then the topographic data coming from the PubDen later, and the bathymetry also coming from the Batnas and Levy. And this is the agent data that we use. As we can see here, this is the simulation. The number of the total population is more than 43,000, and then the number of the car is about the 2,083 cars, and then for the motorcycle is 7,571 motorcycle. With all this data, and then they each have their speed, and then we will have the percentage for each mobile and car and motorcycle. In this simulation, we use the scenario, which is 5 minutes after the origin time, where BMKG disseminate quick information and tsunami warning within 3 minutes, and in 2 minutes, a panic situation. And then all the pedestrians are assumed to be at home, and 25 stochastic simulation. And also we will have the comparison between the population who has knowledge about the location of the shelter, and they don't have knowledge about the location of the shelter. And this is the tsunami simulation result. We will have the maximum tsunami height with a 32 meter, and the tsunami arrival time is 21 minutes. And also there are tight gates virtual in this simulation. This is the agent-based model that we have. We can see from the left side of this panel. This is the adjustable parameter that we can use. The adjustable parameter will be consist of the number of the kid, number of the elder, number of the adult people, and then also we can adjust for the time for the simulation. And then in the middle is the time for during the simulation. And on the right side is this, the comparison between how many people decide to take evacuation and how many people to be casualties, and also how many people to be saved. And this is the initial condition that we have done during our research. First is the initial condition, where we can see from here that the agents are at their house before the tsunami come, where the orange one is the motorcycle, the yellow one is car, the black one is pedestrian, and house the gray color, and the evacuation site to be on the rectangular red, and exit is the yellow box. And this is the situation when the end of the simulation. We can see the conjunction area that show on the white page. On the red page means the casualty area. And this is the simulation. We can see for 60 minutes that we ran this model. And this is the result. From this graph, we can see the average casualty within the people or the population who has knowledge, called the random who doesn't have knowledge, called the random shelter on, using as the pedestrian or using the vehicle. And then the number of average casualty for the people who have knowledge, called the random shelter off, within around 69% pedestrian and 85% for the vehicle. And then with the agent who knows the location of the shelter, it will be, it can reduce the casualty within 4 until 11. And then this is the evacuation site demand. We can see here, agent attempt to evacuate to TB3. TB means Tsunami Evacuation Building 3 as the Pelabuhan Ratu Sports Center and the exit 3. And the last, the conclusion is tsunami trigger with a magnitude 9.1 located in Pelabuhan Ratu would have more higher fatality rate compared to the 2004 Aceh tsunami. And then the second one is due to the limited evacuation site, might urge the use of vehicle for evacuation. So, however, the vehicle will have higher risk casualty compared to the pedestrian. And the last is the research can suggest potential community to enhance tsunami disaster mitigation in the future. Thank you very much.
Thank you very much for excellent presentation, Dr. Venezia. And the next speaker, please. And the talk is about the lakes in the Tibetan Plateau and associated floods. Yeah, thank you.
Hello? Yeah, good afternoon. I'm Yuni. Today, I just want to talk about glacier and also glacier lake outburst floods. And this work has been done by the national team, including my colleague from my institute, like Professor Kang, and also international contributor, just like Richard from UK and others. Yep, I just want to start from this picture. You can just see that the lake, this is a typical glacial lake. Actually, we just defined glacial lake and formed by glaciation. We can just imagine then, just in this area, it was just covered by glacier, but as global warming and glacial lake formed. And why we just care about glacial lake? One thing, they are one kind of water resource and also sensitive to climate change. Last, most important, it refers to glacial lake outburst flood. Okay, we can just see some historical globes events just here, like Marco or just Komatogacho. Okay, just those events just cause huge damages. Just like Komatogacho, it caused economic loss up to $300 million. That equal to almost just 20% of Nepalese GDP. So we just want to know how to minimize the impact of globes. However, we face the many challenges. One is the lack of knowledge, because glacial lake just distributed and the high elevation area, just like the Kashmir, it's not easy to be there. So just the inadequate understanding of the outburst mechanism just leads to unreliable risk assessment. And especially just like the Tibet Plateau, our study area focused on this area because this is region is among most vulnerable globally to globes. And this area also very important to China, also just surrounding countries. So we just leave efficient and automated method just to identify historical globes. And this just provide information for risk assessment modeling. So we just provide a fully automated framework just to map lakes. Here we can see just including forecasts, just including just data precipitation, also modeling training and selection, and just create some masks. Also include just data post-process. Those steps just guarantee that to create a high quality glacial lake data. So to train this modeling, we just select Hiddekus, Karakoram, and Himalaya as a case study just to train our model. And for those areas, just include some key steps, just like to optimize the unit model, and also just to create some mask, just like cloudy and seasonal snow, and also topographer schedules. We must remove the impact from those. And here we can just see some example as we can just actually just to extract this mark and then just to remove their impact. Our results just show that the mapping method is able to create a rational inventory of glacial lake. We can see just the lake distribution, also the vegetation. And then we just propose a lower automatic algorithm just to accurately monitor the state of glacier. And we can just detect individual glacial lake. Once we just input the remote sensing data, and then we can just detecting anonymous, and then we just remove the anonymous and just try to create a high quality glacial lake for individual data, and then we can just monitor the status. So we can just automatically to extract the glacial lake, and then we just developed a new, just a generic framework to investigate like more in-depth globes. This one, this the types of globes. Here is just the framework, and then we just to make some modification and to make this framework is suitable to investigate get just like ice stamped gloves. So there are two types of gloves. So we have to just make some revision and then just make all those models suitable for so just the input the critical parameter are different for those two models. Finally, we just to create the historical gloves database. Since our results just show that like Asian gloves increasing just over time, and we can categorize the gloves into three types. One we just call the more damaged. This is the most severe type, and especially just occurred in the Himalaya. Another we call it just ice-stamped gloves. This is the most frequent and primarily just occurred in the Karakoram. And then we just call the others. That means just the lake just inside the glacier. This type of gloves has been paid less attention due to the limited water volume. However, very recently, gloves just change our traditional viewpoint. Just the gloves this July, yeah. A gloves just from Super Glacier and in-glacier lake or Probe Glacier just cause significant damage to the tree. Here resulted tens of fatality as well massive just losses. We can see just destroyed a bridge, and this bridge just link China and Nepal. Also, we can see just destroy the downstream market, road, and the vehicles, something there. Here is just a typical more than we call it just barbaric leg gloves, and this is one of the most severe gloves, because it caused about 6,000 fatality. Okay, this is the ice-stamped gloves. Okay, just about in 2022, it just saved just the Karakoram highway, so it impacted the international trade between China and Pakistan. So, finally, I just want to talk about the future of gloves. Okay, this refers to just climate change, also glacier status. We just want to know gloves trade. It is unchanged, decrease, or just increase it. We want to just answer. But from my understanding, it is very likely to increase just in the near future. And by the way, just the increasing exposure and global hazard significantly just threat to Asia's economic development, especially just in the mountain area. So, what action should policymakers just take? Just for Huangxi, maybe just the stakeholder just have to just invest to scientific research, and then just to enhance just the risk prediction. Nothing just create a monitor network, just maybe just integrated satellite observation, aerial, also just ground observation to reduce future casualty and damage to infrastructure. Finally, maybe try creating a real-time platform for shared data, hazard data. The cross boundary is a large choice just to reduce the damage. That maybe just cause the transboundary effect. Here is my team. Thank you for listening.
Thank you very much, Dr. Yang Nei, for interesting presentation. So we move to the next one. And Dr. Shi Xu is presenting his talk, which is rainfall over Tibetan Plateau, the bias in summer rainfall. Thank you very much.
Thank you for your introduction. Okay, good afternoon, everyone. I'm Xin Xu from Nanjing University. Today my talk is about actually about the atmospheric sciences, about the orographic gravitative drag parameterization in the models and its impact about the simulation of rainfall over the Tibetan Plateau. Okay, next please. Okay, rainfall is very important over the Tibetan Plateau for the weather, the climate, the hydrology, and for the ecosystem. However, the accurate simulation of the rainfall is very difficult over the Tibetan Plateau. The model often produces too much rainfall over the southeastern Tibetan Plateau, which is a long-standing problem from the early years of the 21st century. Okay, next please. There are many reasons for this problem. One of the reasons is the model cannot accurate to represent the effect of the complex terrain over the Tibetan Plateau. For example, the complex terrain can induce many orographic drag effects like the flow blocking, the lee wave drag, and the TOFD, and the gravity wave drag, which is a focus of our study. Next, please. Yeah, next. Okay, gravity wave is generated as a stably stratified airflow disturbed by the underlying topography. These waves are generated in the near the surface, but they can propagate vertically to the stratosphere and even the mesosphere. And as these waves break, they can deposit the wave momentum into the mean flow, producing a drag force known as orographic gravity wave drag. Next, please. And because these waves are very small, so they often need to be parameterized in numerical models. And the current OGWD scheme often assume assumption of the so-called dry air assumption. However, as we know, there are plentiful water vapor over the Tibetan Plateau. That means there is a lot of moisture, and the phase change of the water vapor and their diabatic processes can significantly affect the atmospheric instability. Thus, they can affect the propagation of gravity waves. However, such effect has not been considered in any OGWD scheme. Okay, next please. Okay, so in light of this, we revised the OGWD scheme developed by Kim and Doyle by considering the moisture effect on the buoyancy frequency. And in the old scheme, it used the dry diabatic assumption, but here in the revised scheme, we consider the moisture effect on the buoyancy frequency from earlier work proposed by Duran and Clamp. Next, please. Okay, when we revise the scheme, we conduct a series of numerical experiments for the summer precipitation over the Tibetan Plateau. We conduct a 20-year simulation in the summer season, and we conducted two parallel numerical experiments. In the control experiment, we use the original scheme, that is using the dry air assumption, and we also conduct a sensitivity experiment, that is the moisture experiment, which consider the moisture effect in this scheme. Please continue. Okay. So this figure shows the simulated precipitation. The first one is satellite observation, and this is precipitation in the control experiments. That is using the older scheme. We can see there are too much rainfall in southeastern plateau. So this is the wet bars, as we clearly shown in the difference between the two experiments. When accounting for the moisture effect, we can see this wet bars is significantly reduced in the moisture experiment. Okay, next please. Well, we know the rainfall is closely related to the water vapor transport, and this figure shows the rainfall in southeastern plateau. The water vapor is actually from the from the ocean, from the Bay of Bengal. Please continue. There's an animation. Yeah, this is water vapor transport. But from the difference, we can see there is a cyclonic circulation. And although the winds are enhanced here, the winds are blocked by the topography, and they turn to westward. So there are less moisture transported to the southeastern plateau. So the wet bars are reduced. So the problem is how the revised scheme affects the wind circulation and the moisture transport. Okay, so we come to the theory. Okay, next please. Well, in theory, the drag is negative, so it is act to decelerate the mean flow. So that means if we have stronger drag, there will be weaker wind, and if we have weaker drag, then the wind will be stronger. This is a direct effect of the drag. Please continue. Okay. However, the drag itself is proportional to the horizontal wind, so that means if we have stronger wind, then we will have stronger drag, and vice versa. So there will be an interaction between the drag and the wind circulation. Okay, next please. So these two figures show the wind difference and the drag difference between the two experiments. We can see there are enhanced wind horizontal wind speed and reduced wind speed here. And in this place, we have the weaker drag, and in this place, we have a stronger drag. So that means the interaction between the drag and the circulation dominates in the summer season. However, at a shorter time scale, that means less than the seasonal scale, this is not always the case. We take the drag and wind in this season, for example. Next, please. Well, this figure shows the temperature evolution of the drag and the horizontal wind. As we can see in the early 30 days, we have the stronger drag and the weaker wind. So this means the drag direct effect dominates in the early 30 days. However, it changed in the following days. We can see we have stronger drag and stronger winds. So this means the interaction dominates in the later stage. So in the early stage, we consider the moisture effect. It will reduce the atmospheric instability. Then we will have a stronger drag, and under its direct effect, the wind will decrease. So this is the direct effect, but we still see some fluctuations of the drag and the wind circulation. This is because the interaction between the wind and the drag. So if the wind decreases, then we will have the weaker drag. The weaker drag will under the direct effect, it will increase the wind circulation. So there will be several loops in the first stage. So, but the question is how the interaction dominates in the following days. This is because at each time of the wind increase, there will be more moisture transported to the ocean. Please, next slide. Then we will have more precipitation over the ocean, and the precipitation will release the heat, which will be induce the cyclonic circulation. And this cyclonic circulation will increase the wind here. So this is well known the CISC scheme. Okay, next please. And the CISC scheme works at a time scale of about 1 month, which can be derived from the scale analysis. It has a special scale of about 2,500 kilometers, and the horizontal wind dispersed is about 1 meter per second. So it works at a time scale about 30 days. Okay, next please. This is confirmed by the model results. The red line is the precipitation difference over the ocean, and the blue line is the intensity of the circulation. In the early days, both the precipitation and the circulation are very weak, but we intensified quickly in the following days. So that means the CISC scheme works at a longer time scale, and it finally dominates the drag and wind circulation in the summer season. Next, please. Okay, so here's a brief summary. We revised OGW scheme by accounting for the moisture effect, and the new scheme can help reduce the wet bias in southeastern Tibetan Plateau through the multi-temporal scale processes. Okay, thank you.
Okay, thank you very much, Professor Jin Shu. And now we finish this part, and we are a little bit behind the schedule, so we have about 10 minutes time for discussion, questions, and comments. Is there any question? No? Yes, please. Microphone.
Can you hear me? I don't have quite a loud voice.
That's perfect.
Thank you. Did you put that parameterization into a regional model, or was it in a global model? And if it was in a global model, do you think it would have an impact on other mountain ranges, not just Tibet?
This is in a regional model, not global model.
Do you think, though, can you speculate about whether that will do a lot for other mountain ranges?
Yes, we have implemented a new scheme in a global model, and it have impact on the larger scale circulation. That is in the northern hemisphere high latitudes, especially in the stratosphere, because the change of the drag can affect the mean flow, and the mean flow will affect the propagation of the Rossby waves. There will be a mean flow interaction. So yeah, it has a global, I think it has a global impact. Okay, thank you.
Any more questions? Yes, please. In the back.
Thank you. I have questions for Mr. Meilano from ITB. Do you also make consideration when you measure that the velocity field of the GPS data set you are using also consider the energy release? Whether the simple logic, we also say that energy accumulation building a potential energy, and then when the earthquake release, it will also reduce the accumulation strain. I think maybe it's better to look whether there is a correlation or not between the energy which was built by the strain velocity and then released by the earthquake events. Because maybe if you use the last 20 years of data, then we also see at the area with strain you explain on your study result that the Banda area at I see some spot on the Flores, and you say that you mentioned also about this Ambon and Seram region. And another question is for Professor Min Feng. I interested on your data set. Maybe I need to get some more explanation about the identification of the periglacial landform. If you use the MT INSAR data set combined to your Deep Lab 53+, and then what spectral and spatial resolution did you use to analyze it? And then you say that we can access this data.tpdc.ac.cn. Is it for free? Maybe we can make an account because you know there's a place in the eastern part of Indonesia, as you may know that there's a huge island there. It's Papua. There's also a plateau there, which rarely been seen to be investigated by scientists. It is in the reeds. It is one of the most popular place to
to visit because it is one of the place in the equator which still have a permafrost maybe. Yeah, it's very interesting. I think maybe if we see this Tibetan plateau is almost as huge as Indonesia, then this small place in this Papua is also interested. Maybe it has same geomorphological characteristic as the Tibetan plateau. Thank you.
Okay, thank you. You had two questions and comments. So please, first, Professor Meilano.
Yes, thank you for your questions. So regarding the time series, of course, it is include not only what we call as interseismic deformations or the time series before the events, but for example, just to give you an idea that it is very in terms of the complexity of the research, most of the data that we have in Sumatra is after 2004. It means that almost all our data set contain the post-seismic deformations of the Aceh earthquakes, the magnitude 9.0 or 9.1. And also we have several big events, for example, Nias earthquake 8.5, which also produce significant post-seismic deformation. So the challenge is we have to model this kind of non-interseismic deformations, and also some co-seismic deformation, the sudden release. So after we model every release of the event and also the post-seismic deformation, then we can have a consistent interseismic strain accumulation. So to answer your questions, we have to carefully investigate our data. You point out very good issue, the sudden drop of the earthquakes. In order to remove the earthquake data is quite easy because we have already the seismic data. We already have the slip distributions from the teleseismic inversions. But to calculate the post-seismic deformation is quite challenging. So we combine the models from the co-seismic together with the post-seismic to produce the consistent model of the strain accumulations or the interseismic models. Thank you.
Professor Ming Peng, please.
Yeah, thanks for the question. That's a very good one. So once after we finished the mapping of Tibetan Plateau, the first thing came to my mind is to see if we can do a larger area, even the globe. Like you mentioned, Indonesia, that should be a part of it. But it's not that easy that we can simply apply the model to it. So there are two things. One is that this kind of approach is called transfer learning. So you build a model in one region and you apply the model to a different region. Sometimes it works, sometimes it doesn't. The two reasons to that. One is that the model may not be sophisticated enough to capture the features so well to fit other region. The second thing is that the second condition is that maybe the second region could show unique features that were never learned by the model built in the first region. So we tried our model in other regions, not Indonesia yet, but like Alaska and Rocky Mountain and even Europe. We can see that we can capture like 60% of the cases, but that accuracy is still too low. So we have been engaging in improving it in those two things. One is that we are trying to apply a much stronger model, which is vision transformer based. So that would be much better than the one DeepLab V3 Plus, the one that we applied when we do the Tibetan Plateau. The second thing is that we are adding more training data globally. So that way we can capture other regions much better. So that's the work that's ongoing, and we would like to see that we can test our model in Indonesia, like you mentioned, the test site. So yeah, that's.
Okay, thank you very much. In order to respect the timing of a schedule, we move to the next part of this session. And if there's any more question, you can do it at the end of session later. So Professor Ming Fen, you already have the microphone. Please continue as a chair.
All right. So in this session, we have 3 presentations left. I'm gonna be chairing those ones. So our first one is from Dr. Song Yong. Dr. Song is from our institute, Tibetan Plateau Research and Academy of Sciences. So his topic is about Indian Ocean warming and Hadley circulation changes.
Okay, thank you. Just show the slides. Please show my slides. First, thanks Professor Ding for this opportunity to share our recent work. This is a collaboration with Gilles Remerston from LSE, Alexei Bedrov from Yale University, supported by Professor Ding. Why we focus on this topic? It's well known that Hadley cell is thermally direct large-scale overturning circulation with running air near the equator, descending motion in both hemispheres. Hadley cell, one of its most important rules is shaping the formation of the subtropical dry zone in both hemispheres. With the global warming, the Hadley circulation is undergoing significant changes, and its impact on climate is drawing increasing attention. Observed evidence show a forward expansion of Hadley circulation since 1979. As the descending branch of the Hadley circulation is closely linked to the subtropical drying zone, so Hadley cell boundary shift would push the shift in the location of this drying zone. In response to public concern on this hot topic, the IPCC and also climate science special issue have included a dedicated chapter to review the latest progress on the Hadley circulation. Although there are general consensus on future Hadley cell changes, for example, expanding of its boundary, weakening of its intensity. However, its underlying driver remains debated. Moreover, recent record-breaking ocean warming is becoming increasingly common. The impact of rapid ocean warming on the climate system is also a urgent issue that needs to be addressed. Next. It's expected that and the continued increase in greenhouse gases emission, ocean temperature will keep rising in the future. The impact of sustained ocean warming on climate system is also a core topic of CLEVA. However, the impact of rapid ocean warming, especially regional ocean warming on the Hadley circulation, remains unclear. And the Paris Agreement temperature threshold, we aim to address the following scientific question. First, which ocean warming, basin ocean warming is dominant the future Hadley cell changes, and which ocean basin warming is the main source of uncertainty of HC projection. We first analyze 6 CMAP-5 experiments, including RCP 8.5, historical, and also 4 IMAP type experiments. In each figure, the first column shows the future AC changes defined as the RCP 4.5 minus historical simulation, and the second column shows contribution from CO2 increase to future AC changes, defined as a map 4 times CO2 minus a map. And the last two columns show the contribution from globally uniform ocean warming and non-uniform ocean warming to the future AC changes. No matter we examine the southern hard cell boundary, northern hard cell boundary, RTC location displacement, or uncertainty in the northern hard cell intensity. All these close links to future SSC changes. This highlights the necessity conducting regional ocean attribution for future HC changes. We first conduct a suite of idealized separate ocean basin forcing experiments. This allowed us to find a target basin that potentially affects the future AC changes. Six basin test basins include tropical Indian Ocean, tropical Pacific Ocean, Northern Atlantic Ocean, Southern Atlantic Ocean, Southern Indian Ocean, and also Global Ocean. In grading, in idealized its management, so hard cell is not highly sensitive to Southern Indian Ocean warming amplification. So we select 5 ocean basins for numerical simulation and 3 warming temperature threshold. This slide shows animation warming patterns of 5 target ocean basins and 3 warming temperature threshold. We next present the distinct AC response to 5 target ocean basin warming. Southern Atlantic Ocean warming drive weak expansion of southern hard cell. Tropical Indian Ocean drive significant forward expansion of northern hard cell. Both ocean warming can drive ITCZ away from the equator, but show the compressing effect on the northern hard cell intensity. Southern Atlantic Ocean warming intensify northern hard intensity, and the tropical Indian Ocean weakens. In addition, the divergent response of the 4 metrics to global ocean warming mainly results from they are inconsistent response to the tropical Pacific ocean warming. Now we can conclude that tropical ocean warming can drive weakening and expanding of northern hard cell, but a driven rule in southern hard cell is not the case. So we further examine the response of northern hard cell and southern hard cell intensity and boundary to tropical Indian Ocean warming in different seasons. This also supports that the driving rule of tropical Indian Ocean warming in weakening and expanding of southern hard cell. Now I'll give a very short conclusion to respond to the 2 questions we raised at the beginning. Tropical Indian Ocean is the main driver of the future AC weakening and expanding in both hemispheres. Second, tropical Pacific Ocean warming is identified as the uncertainty source of certainty in future projection. Okay, thanks.
Thanks, Dr. Sun. Our next presentation is from Ida Pramodani. The topic is about weather drivers and their roles in disasters.
So, hello everyone. So this is my presentation today about the multi-scale weather drivers and their role in hydrometeorological disaster in Indonesia. So before we go into detail about what I want to share today is I want to show you the frequency of extreme weather across Indonesia during last 3 years. So this is the condition of Indonesia disaster event. We have more than 6,000 total events, especially in the area of West Java here. So, and it followed by Central Java, so we can see the heavy rainfall generally occur very significant that also can threat Indonesia region. We also have a tropical cyclone event, even though this tropical cyclone not crossing Indonesia region, but indirect impact also cause Indonesia and cause disaster in Indonesia. So. And I think BMKG College are already familiar with this, but I think it is also important for you who for the first time see this image. So we can see that throughout the year, Indonesia have a threat for a hydrometeorological disaster, like during December, January, and February, which is a rainfall season in mostly Indonesia region. We have floods. So the threat will be floods and then landslide and also high wave. And during June, July, and August, which is a dry season, we have a forest fire and then drought and also high wave as well. And then during a transition, like in March, April, May, and also September, October, and November, we have a different extreme weather event like hail, then a small tornado, we said it puting beliung in Bahasa, and also we have a very frequent thunderstorm in Indonesia. So this is the multi-scale weather drivers in Indonesia. So we have a at least 4 multi-scale weather drivers, like a global, synoptic, mesoscale, and also local scale. For a global scale to a synoptic, we have El Nino, and then we have a sea surface temperature with a high anomaly of sea surface temperature can cause a big or a lot amount of evaporation in the Indonesia region that can cause the increasing of heavy rainfall. And then we also influenced by the Indian Ocean dipole that contribute from the Indian Ocean, and it influenced the western part of Indonesia. And then we have weather drivers from the ASEAN monsoon and Australia monsoon, Madden-Julian oscillation, equatorial wave, including equatorial Rossby and also Kelvin wave. Sorry, it is still in Bahasa. And also the ASEAN cold surge, which when it accompanying the ASEAN monsoon, it can increasing the rainfall in especially in Java Islands. And then the last but not least is the tropical cyclone. And over there is a convection process in Indonesia. Because we are in the tropic, Indonesia lies in the tropic, so local meso to local scale is influenced very significant for Indonesia weather condition, like such as the convection process. So those images show us the mechanism of a convection process in Indonesia. And the picture below showing us the distribution of rainfall captured by radar imagery. We can see even not spread evenly, but we can see there are a spot that showing convection happen in region of Jakarta. So for local convection usually occurs during the transition period in Indonesia or during a change of season and have at least three characteristics with a short duration, accompanied by lightning, thunder, and strong wind, would have a short period, and then the last is sometimes cause hail and also tornado. So this is an example of several Indonesia's extreme rainfall in past 5 years. So in Jakarta, during 2020, 1st January, we can see very extreme rainfall occur in Jakarta, reaching 377 millimeter per day. We can imagine the damage caused by the extreme rainfall at that time. And then during the February 19 in 2021, Jakarta also occur heavy rainfall reaching 226 millimeter per day. And Jakarta, I think it is very early this year, in March 3, 2025, the rainfall accumulation reaching 232 millimeter per day. And also in Bali, not only in Jakarta, in Bali, we also experiencing a very heavy rainfall in September 10, 2025, because the extreme rainfall reaching 385 millimeter per day. And there are several disaster impact causing by extreme weather condition, like flooding, total drainage failure, widespread disruption of infrastructure, and etc. And the picture show us also in the right below. We can see damage caused by extreme rainfall in Bali. So I want to show you several cases for flooding in Indonesia region, not flooding, but also hydrometeorological disaster caused by the weather condition in Indonesia region. This is a first example in Jabodetabek. We can see during the New Year Eve 2020, we can see a very extreme condition happen in Jakarta at that time. And we can see the impact, including flood in every place in Jakarta, west part of Jakarta, south, east, and north part of Jakarta. We are flood because by the heavy rainfall. And based on the research by Lubis in 2020, there are several factors that contributing for the disaster at that time in Jakarta. Because the extreme rainfall condition, the first is Asia cold wave, and the second is equatorial wave, which is combination between the mixed Rossby gravity wave, MGO, then Kelvin wave, equatorial Rossby, and TD type, and then Madden-Julian oscillation. So this is for the case number 1, hydrometeorological disaster caused by Thesis Roja. We can see several pictures here and several impact caused by Thesis Roja. We see the extreme rainfall accumulation due to the tropical cyclone Seroja. This is a horizontal structure of the first intensification of Thesis Roja, because Thesis Roja have a two intensification phase. The first intensification giving a damage for Indonesia region, especially in eastern Nusa Tenggara. So this is the horizontal structure here. We can see a vertical velocity. In the left one is for a low level, and right one is for a higher level, 150 hectopascal. For low level, we can conclude that a well-defined updraft accompanied by low-level convergence was observed on April 3rd, and it became narrower and more concentrated over the western to northern portion of disturbance on April 4th to 5th. And for the right one, the strong updraft still persists until the upper level around the system center, although the outflow already formed as evidence of a strong tropical cyclone development stage. And then this is also the horizontal structure. We can see the outflow. I think I have to go faster. This is, sorry. Can we go back to the previous? So this is the structure on the first intensification of tropical cyclone Seroja. We can see the track and we can see the structure, vertical structure of tropical cyclone Seroja. Can I continue? And then the first slide, please. Can you help me? So this is the simulation of atmospheric drivers influencing weather condition in Indonesia during this rainfall, this rainy season. So there are at least 6 phenomena that can influence the weather condition in Indonesia in this rainy season. The first is a weak La Nina, and then negative IOD, a significant high pressure area over Siberia, and also low pressure area in Australia. The fourth is about the activation of ASEAN monsoon accompanied by ASEAN cold surge, and then the active of MGO and convectively coupled equatorial wave, including Kelvin, equatorial Rossby and mixed Rossby gravity, and the last one is tropical cyclone that active during this season in the southern hemisphere. I think that's my last slide. Thank you.
All right. Thanks, Ida. And our next presentation comes from Dr. Supari from BMKG. His topic is about anomalous weather conditions of the 2025 dry season. Because Dr. Supari cannot physically be here, we have a room session set up for him. Yes, we can hear you.
Thank you. So I start now?
Yes.
Okay. Thank you, moderator. I would like to share our analysis possible mechanism of what we just experienced here, the anomalous weather condition of the dry season for Indonesia, and specifically for Java Island. So I know this is late day and maybe our energies already start to drop, but I hope I still can get the attention from this one. So this is the background of our analysis. So if you look at here, this is the rental of Indonesia. It presented as a percentile in respect to its historical data. So green means that above normal condition, and brown means below normal condition. Look at this is February, March, April, May, June, July, August, September, October. So what interesting from this actually during May to July, it is the green color illuminated over Java Island. This is Java Island. This is Sumatera, Kalimantan. Even though the weather condition actually continue up to this November, but I would like to focus only on Java Island. This is the histogram of rainfall accumulation during May to July over the last 45 years. Look at here, 2025 is the 4th wettest May to July, confirming that this rainfall condition is not usual event. So if you look at the media and also social media, you can get information that public also respond this condition by discussing in the social media. For example, during May, June, our sentiment analysis say that the dominant posting from the netizen is when will the dry season take place? Because May normally should be a dry season of Indonesia, but this year we have still much rainfall for May, June, July. So this is part of the system temperature of a tropical area. Just we from us that actually during April, May, June, Japanese atmosphere. It is part of the transport water vapor that we get for Java Island. This is April, May, June, July, August. There is again Israeli transport of water vapor. So water vapor coming from east part going to the Java Island. And the next question is what is the driver of this anomalous condition? Because actually the global climate status is very bad. Because every talk about Indonesia, usually the driver of the anomalous climate condition is coming from ENSO or the IOD. But every correlate spatially between rainfall over Java Island and the global test, okay, we got like this. So rainfall over Java Island significantly correlates with the local sea surface temperature. So this is significant. But start from August, we got the negative correlation between Java rainfall and the Pacific Ocean, meaning that the contribution of the ENSO quite significant for Java Island in this period, August and also September. And this small relation, despite that actually still get even forward lifetime correlation, meaning that sea surface temperature of local waters in Indonesia influence the next month rainfall project. And also, if we look at more detail, there is an area where consistent we have significant correlation. So this is rainfall of Java Island, and this box of the sea surface temperature consistently appears in the correlation analysis. So if we try to plot the time series of per year and also sea surface temperature of per year, then we will have the line graph like this. So every warming of the SSA, the red color is for SSA, we will have the increase of rainfall. This is the example of 2016, which is the wettest May to July rainfall of period last 45 years. And so this is 2022, this is 2013, and this is 2010. But this year is not always linked with the global phenomena such as ENSO. For example, 2013 is the metal year, and also this is example in this year, 2025. And this is a kind of analysis to compute the contribution of ENSO, IOD, and I also add the GBO as global phenomenon, and also sea surface temperature anomaly for the Bali sector of the Indian Ocean. We will get this number, which is the local SSA contributes more than 50% to explain the variation of the Java rainfall during May to July. This confirms that this local sea surface temperature significantly give large contribution to the rainfall of the Java Island compared to the ENSO, compared to the IOD, especially during May to July. So actually, what is the cause or the mechanism of the warming of this area? In 2022, Sankili proposed small-scale climate mode named Java Sumatra Nino, which is characterized by the warming of SST over this area, and it influenced rainfall over Java. And this is the example from three highest May to July rainfall. This is 2016, 2015, and also 2010, and also 2010. And if you plot the SST and also where the value of this wall, you can consider that the warming is clear and the impact to the Java rainfall will be from the rainfall data. So the summary of this presentation, we have what anomaly of the dry season over Java Island during this year, 2025, this May to July. And interestingly, this MDG above normal rainfall occurred during April, based on the edge of IOD. And this trigger equation, so what is the driver of this buffer condition and possible mechanism, one of the possible mechanisms is warming for the value sector of the erosion, which proven by the historical data that plays from last contribution which can enhancing this year of the chapter. So that is all of my presentation. Thank you for that knowledge.
Thanks, Dr. Supari. That'll be all of our presentations. Now we can have a few questions. Any questions to our presentations? Yes.
Really interesting talk and really interesting results. Two sort of parts of my question. One is, do you really understand the mechanism why the Indian Ocean is so effective at moving the Hadley circulation and the changes? And also, is there any interaction with things like the IOD? Is that also important?
From an IOD warming, yeah. Okay, I think I almost answered the question.
All right, any other questions?
Hi, Young. So I'll ask you another question. Did you look at the response over land in the similar regions of what the ITCZ will do? Is it quite similar or a bit more varied?
You mean that the land response here?
Well, yeah. Do you see
local response here?
Yeah.
In fact, we also examine the globally the mean hard cell, not focus on not examine the regional hard cell or the local hard cell response to different ocean basin forming in our society. But this is also very important thing to do this in the future. Yes, thank you.
Great, thanks.
We have a question over there.
Yes, my question for Professor Irwan Milano. What are the strengths and limitation of geodetic method in estimating slip deficit on Indonesia megatrust zone? Thank you. Professor Irwan Milano. Pak Irwan, what are the strengths and limitation of geodetic method in estimating slip deficit on
Indonesia Megatrust Zone.
Yes, I'm going to give a quick answer, then we may have detailed discussion after this. The most obvious limitations of geodetic data to constrain or to estimate the slip deficits in the megatrust zone is most of the data come from the inland side. So we don't have the data or the onshore observations of the deformation, which is somehow, if you are familiar with the inversion or parameter estimations approach, so then we have what we call as one-side geometry to calculate the parameters, which is it is quite difficult. So one of the most obvious limitations of using GPS data is the distributions of the data itself, because the data come from the inland side, while we have to estimate the slip distribution or the coupling distributions on the subduction interface, which is located sometimes quite far from the observation site.
Yeah.
I hope I answer your question. Then we may have detailed discussions.
Okay, many thanks, Professor.
Welcome.
All right. Any more questions? No? Oh, okay.
I have one question for Professor Erwan Meliano. Is there any sign of creep in the subduction zone from your data? Thank you.
Well, yes, if it is associated with the after sleep, we do have. If you are mentioning the creeping process is associated with the after sleep deformation, we have such a clear evidence of this creeping soon after the earthquakes. But we also found a creep. Probably it is associated with something else that's not related with the after sleep of the earthquakes, but it is not. We don't really understand the signal yet. I mean, of course, we already tried to model with several processes, but we are still working on that part. Probably it is related with the slow sleep event, which is we found in many area of the subduction area. Probably something else, but to answer your question, yes.
Thank you, Professor.
All right. Any other questions? All right. Professor, you have anything to add? Okay. If that's the case, so we will end our session and give it back to our workshop. Thank you, everyone.
Yeah, also thank you all the organizers. It was great pleasure to be here. So we pass the stage to closing ceremony. I don't know who is going to, Professor, are you? Oh, you go ahead. Okay, thank you very much.
Thank you very much. Ladies and gentlemen, on behalf of the committee, we would like to give our biggest appreciation to all speakers in session 5 and also in other sessions. It was a very good presentation, and it was an honor for all of us to learn something new from all of you. The next is, I would like to invite Deputy for Geophysics, Mrs. Nelly, to award a souvenir as a token of appreciation from us for the last keynote speaker, Professor Irwan Meilano. For Mrs. Nelly and also Mr. Professor Irwan Meilano, please come forward, and for the documentation team, please get ready to take a picture. We would also like to invite Professor Linding to come forward to accompany the process and also take the picture. All right, thank you very much. You may be seated again. Ladies and gentlemen, 2 days feel like a short, very short time. We have watched all 46 talks from all distinguished speakers, and we wish that we all be benefited from this event. Now we have arrived at the end of this event. We will hear several closing speeches from representatives. The first is, I would like to invite Professor Xin Li as the Deputy Director of Institute of Tibetan Plateau Research, Chinese Academy of Sciences, to give a closing speech.
Good afternoon, distinguished colleagues, ladies and gentlemen, and our great hostess at BMKG. On behalf of the Institute of Tibet Plateau Research, Chinese Academy of Sciences, it's a profound honor for me to express my warmest congratulations on the successfulness of the second PlateauPlus workshop. First and foremost, I would express my deepest gratitude to BMKG. Your team has done a magnificent job organizing this event. The partnership between our institute and BMKG is a shining example of cross-border scientific cooperation. By hosting us here, you have not only provided a venue, but a bridge connecting the high mountains of Asia to the complex archipelagic geology of Indonesia. I also want to thank every scientist, research, and students attending this workshop. Many of you have traveled far away to be here. Your presence confirms the science knows no borders and that questions we are asking are of global significance. We are meeting at a pivotal moment, as many of you know. In May 2025, just this year, the PlateauPlus initiative achieved a major milestone. We were officially endorsed as a program of the International Decade of Sciences for Sustainable Development under UNESCO. This endorsement is not just a badge of honor, it's a mandate. It signifies that the international community recognizes plateaus are not merely isolated geographic features. They are the water towers of the world, the drivers of regional climate, and the home to unique and often fragile ecosystems and human cultures. The Institute of Tibet Plateau Research remains steadfast in its support. We are committed to providing the resources and backing necessary to ensure that PlateauPlus continues to thrive. We will continue to support future workshops and actively promote this initiative on the global stage, ensuring it becomes a central pillar of international earth science cooperation. Looking ahead, I see PlateauPlus playing a critical role in uniting scientists worldwide. This initiative is an open platform. It's a home of those who wish to understand the pulse of the earth through its highest elevations. In closing, let us dedicate this workshop to the spirit of collaboration. Let us work together to promote the PlateauPlus initiatives as a beacon of global plateau research. Thank you so much.
Thank you, Professor Sin Lee, for the closing speech. The next is I would like to invite the State Key Laboratory of Tibetan Plateau Earth System, Environment and Resources, Institute of Tibetan Plateau Research, Chinese Academy of Sciences, the Director of TPESER, Professor Lin Ding, to give a closing speech.
Okay, now we stand at the end of the second PlateauPlus workshop. Honorable Dr. Nelly Florida Rima, dear Diana, Director of the GFX, all participants in this room and online. First of all, I would like to once again extend my heartfelt thanks to BMKG and specifically to Professor Koto Fatani, Dr. Nelly Florida Rima, and Dr. Diano for their expectation leadership and warm hospitality. You have made Jakarta feel like a second home for all PlateauPlus family. A special thank you go to the organizing committee, Bagus, Fanping, Jian, Sushi, and to all the team members from both BMKG and ITP KAIS. The success of this event is a testament to your hard work and seamless coordination behind the screen. With Bagus, with Pingfan, Jian, and Sushi. Yeah, please stand up. Let's give them the warmth applause. To all our speakers and participants, thank you for your valuable, insightful, and active engagement. Through this workshop, we have not only deepened our scientific understanding of the TTS domain and multi-hazard risks, but also built a strong foundation for future collaboration. We are pleased to share that this workshop has brought together around more than 200 participants attending in this room and about more than 100 participants joined online. Totally, it's more than 300 participants. This reflecting the enthusiasm and importance of this international scientific forum. Moving forward, I look forward to expanding our partnership between ITP KAIS and BMKG through joint research, capability building initiative, and a future workshop. Lastly, we warmly welcome future scientific exchange, including continued dialogue in Beijing. We are excited about the opportunity to meeting again and strengthen our cooperation future. Let's carry this momentum forward. I wish you all a safe journey home and look forward to seeing you again at the next PlateauPlus gathering. Yeah, we will figure out the place for the third PlateauPlus workshop.
soon. Yeah, thank you. 谢谢。Terima kasih.
Sama-sama. Thank you very much, Professor Linding, for the closing remarks. The last is I would like to invite Deputy for Geophysics of BMKG, Dr. Nelly Florida Riyama, to come forward and also to formally close the event.
Good afternoon, everyone. I want to see your smile. Yeah, distinguished ladies and gentlemen, first of all, I would like to say congratulations and thank you to all speakers, panelists, and participants for the successful completion of the second PlateauPlus International Workshop. We are very grateful to learn a lot of things from high-quality presentation, insightful discussion, and active engagement that made the workshop meaningful. For me, myself, I think it is my first time to engage with the PlateauPlus, and maybe for some colleagues from Indonesia also our first time, and we are very honored that Professor Lin give us opportunity to host this event. And as Professor Lin mentioned that we don't know yet where the next workshop will be conducted, but we are very eager. Maybe we can gather together again and you can invite us, or yeah, or maybe someday we will host this workshop again. It's because it's very important for us to have your insight and to connect with you all. And of course, we also want to convey our deepest apology for any shortcomings, inconveniences, or limitation that may have occurred throughout the event, since we were welcoming you at the airport. And we hope that the discussion during this workshop and the connection that emerged from this event will continue through future collaboration, whether in joint research projects, scientific exchange, capacity building initiative, or cross-disciplinary partnerships. Of course, this is not the end of our connection, but again, I would like to also encourage all participants to stay connected and continue contributing to the PlateauPlus network. And I wish everyone success in our ongoing work and a safe journey home. At the end, I would like to officially close the workshop and thank you everyone again for your participation. Thank you very much. Please give big applause for us all. Thank you.
Thank you very much, Dr. Nelly Florida Riyama, for closing the event formally. Ladies and gentlemen, again, on behalf of the committee, we would like to say our biggest appreciation to all speakers and also participants for following this event until the end. And we wish that everyone gain new insights, knowledge, and also precious connection from this event. I would also like to repeat regarding the field trip tomorrow. If you feel that you have not registered yet, please do so now after this at the front desk over here. And we also invite foreign guests to join the dinner tonight. The car will pick us up at 5:30. And the last is, I'm Akmal, representing the whole committee, would like to say our sincere apologies for any inconveniences that you may experience during this whole workshop. Thank you, and maybe see you again next year. So while we still have some time, maybe you would like to see the posters that is around you. Thank you. Mas Arfan nama field trip ya?